Hello. I hope you are comfortably settled. Tonight, we are following the complete life of a star, from the moment gravity first pulls hydrogen together in the cold darkness of a molecular cloud, to the final silence that comes billions of years later, when fusion stops and the remnants cool into the void. Every atom in your body was forged inside a star. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it came from stellar furnaces that burned, collapsed, and scattered their elements across the galaxy. We will begin in the dark nebulae, where clouds of gas and dust slowly collapse under their own weight. From there, we will watch as protostars ignite, as main sequence stars burn steadily for billions of years, and as massive stars race through their fuel in cosmic blinks. We will witness supernovae, the birth of neutron stars, and the formation of black holes, places where space-time itself is torn apart. And we will end in the far future, where the last white dwarfs fade into darkness and the universe grows cold. If these quiet explorations help you rest, please consider liking and subscribing. It helps others find their way here, to this calm corner of the cosmos. Now, let us begin at the beginning. In the space between the stars, where the temperature hovers just a few degrees above absolute zero, something extraordinary is about to happen. In the vast darkness between the stars, where light travels for years without touching anything solid, there exist enormous structures of gas and dust so cold that they hover just above absolute zero. These are molecular clouds, and they are the birthplaces of every star that has ever existed. The temperature within these clouds ranges from 10 to 20 Kelvin, which translates to roughly minus 260 degrees Celsius. At such extreme cold, atoms move sluggishly, barely vibrating, their kinetic energy reduced to a whisper. This frigid environment is essential because heat is the enemy of star formation. Warmth creates pressure, and pressure pushes outward, resisting the inward pull of gravity. Only in these cold nurseries can gravity begin to win. A typical molecular cloud spans dozens to hundreds of light years across and contains enough mass to form thousands, sometimes millions, of stars. The Orion Molecular Cloud Complex, located approximately 1,300 light-years from Earth, stretches across hundreds of light-years and holds roughly 200,000 times the mass of our Sun. Within its boundaries, new stars are forming at this very moment, their light not yet visible to human eyes because they remain shrouded in the dense cocoons of dust that gave them birth. The primary ingredient of these clouds is molecular hydrogen, designated H2, which accounts for roughly 73% of the mass. Helium contributes another 25%. The remaining 2% consists of heavier elements, what astronomers call metals, including carbon, oxygen, nitrogen, and silicon. These trace elements may seem insignificant by mass, but they play crucial roles in the chemistry and cooling of the cloud. Dust grains, tiny particles of silicates and carbon compounds measuring less than a micrometer across, make up only about 1% of the cloud's mass, yet they are essential to the star formation process. These microscopic specks provide surfaces where hydrogen atoms can meet and bond into molecules. Without dust, the molecular hydrogen that defines these clouds could not form efficiently. The grains also absorb ultraviolet radiation from nearby stars, shielding the cloud's interior from the heating effects of starlight. The density within a molecular cloud varies enormously. In the diffuse outer regions, there may be only a few hundred molecules per cubic centimeter. This sounds like a substantial amount, until one considers that the air we breathe contains roughly 25 quintillion molecules in the same volume. Even the densest cores within molecular clouds, where stars are actively forming, contain only about 1 million molecules per cubic centimeter. By terrestrial standards, these clouds represent a vacuum more perfect than anything achievable in laboratories on Earth. Yet despite this apparent emptiness, the sheer scale of molecular clouds means they contain tremendous amounts of material. The mass accumulates across light years of space, and gravity, patient and relentless, begins to gather it together. The internal structure of a molecular cloud is far from uniform. Turbulent motions, driven by supernova explosions, stellar winds, and the rotation of the galaxy itself, create a complex web of filaments and clumps. Observations from the Herschel Space Observatory revealed that molecular clouds are threaded with long, narrow filaments of denser gas, typically about 1/3 of a light year in width. These filaments act as channels, funneling material toward the densest regions where gravitational collapse can begin. Within these filaments, denser concentrations called cores develop. A typical prestellar core measures roughly 1/10 of a light year across and contains between 1 and 10 solar masses of material. The temperature at the center of such a core drops even further, sometimes reaching as low as 6 or 7 Kelvin, because the surrounding dust blocks external radiation, and the core's own thermal emission carries energy away into space. The physics governing these cold environments involves a delicate balance. Gravity pulls inward, attempting to compress the cloud. Thermal pressure, generated by the random motions of molecules, pushes outward. Magnetic fields thread through the cloud, providing additional support against collapse. Turbulent motions create localized regions of compression and rarefaction, like waves passing through water. For a cloud or a portion of a cloud to collapse and form stars, gravity must overcome all these opposing forces. This requirement defines what astronomers call the Jeans mass, named after the British physicist James Jeans, who first calculated it in the early 20th century. The Jeans mass depends on the temperature and density of the gas. Colder gas has lower thermal pressure, so smaller masses can collapse. Denser gas has stronger self-gravity, again allowing smaller masses to collapse. In a typical molecular cloud at 15 Kelvin with a density of 10,000 molecules per cubic centimeter, the Jeans mass works out to roughly a few solar masses. This means that any clump of gas exceeding this threshold will begin to contract under its own gravity, provided other support mechanisms like magnetic fields and turbulence do not prevent it. The collapse does not happen quickly by human standards. The free fall time, the duration required for a cloud to collapse if gravity were the only force acting, depends on the density. For a typical molecular cloud core, this timescale is approximately 100,000 to 1 million years. The process unfolds with glacial patience, imperceptible on human timescales, but rapid by cosmic standards. As a core begins to contract, its density increases, which shortens the Jeans mass. This means that smaller subregions within the collapsing core can themselves become gravitationally unstable. The original core fragments into multiple smaller cores, each destined to form its own star or stellar system. This fragmentation process explains why most stars form not in isolation, but in clusters, siblings born from the same parent cloud. The Taurus molecular cloud, located about 470 light-years from Earth, provides an excellent laboratory for studying these early stages. Its relatively low density and isolation from massive star-forming regions mean that collapse proceeds gently, producing mostly low-mass stars. Infrared observations reveal dozens of protostars in various stages of formation, their light reddened and dimmed by the surrounding dust. In contrast, the Orion Nebula, the bright patch visible in the sword of the constellation Orion, represents a more violent environment. Here, massive stars have already formed, and their intense radiation is sculpting the surrounding cloud, creating dramatic pillars and globules of dense gas. The famous pillars of creation in the Eagle Nebula, though not in Orion, exemplify this process, where stellar radiation erodes the cloud while simultaneously triggering new collapse in the densest regions. Carbon monoxide, though present in only trace amounts, serves as the primary tool astronomers use to study molecular clouds. Molecular hydrogen, despite being the dominant component, is nearly invisible at the cold temperatures found in these clouds. It lacks a permanent electric dipole moment, which means it cannot emit radiation efficiently at low temperatures. Carbon monoxide, by contrast, has a small dipole moment and emits radio waves at a wavelength of 2.6 millimeters when its molecules transition between rotational energy states. By mapping this emission, radio telescopes can trace the distribution and motion of gas throughout a molecular cloud. Other molecules provide additional information. Ammonia, with its characteristic emission at 1.3 centimeters, serves as an excellent thermometer, allowing astronomers to measure temperatures within cloud cores. Formaldehyde, methanol, and even complex organic molecules like amino acid precursors have been detected in molecular clouds, hinting at the chemical richness that will eventually be incorporated into planets and perhaps life itself. The magnetic fields threading through molecular clouds deserve particular attention. These fields, though weak by terrestrial standards, measuring only tens of microgauss compared to Earth's field of roughly half a gauss, exert significant influence over the diffuse gas. Charged particles, primarily ions created by cosmic ray impacts, are tied to the magnetic field lines and drag the neutral molecules along with them through collisions. This coupling provides support against gravitational collapse, slowing the star formation process. Over time, however, a process called ambipolar diffusion allows the neutral gas to slip past the ions and drift inward. The timescale for this process is several million years, much longer than the free fall time. This explains why molecular clouds do not convert all their gas into stars immediately. Only a few % of a cloud's mass forms stars before feedback from those stars, in the form of radiation, winds, and eventually supernovae, disperses the remaining gas. The journey from cold molecular cloud to blazing star is one of the most fundamental transformations in the universe. Every element heavier than hydrogen and helium was forged in the cores of stars that themselves condensed from clouds like these. The calcium in bones, the iron in blood, the oxygen in every breath, all of it passed through this cold, dark phase before being processed in stellar furnaces and scattered back into space. In the quiet depths of a molecular cloud, far from any source of warmth, gravity is always working. Slowly, inexorably, it draws matter together, increasing density, raising temperature, moving toward the moment when nuclear fusion will ignite and a new star will be born. The process has repeated itself billions of times across the history of the cosmos, and it continues tonight in clouds scattered throughout the Milky Way and in galaxies beyond counting. The question of when a cloud begins to collapse is not a matter of chance. It is governed by precise physics, a balance between two opposing forces that determines whether a region of gas will remain stable or begin its inexorable contraction towards stellar birth. This threshold was first described mathematically by the British physicist James Jeans in 1902, and the critical mass required for collapse still bears his name: the Jeans mass. Within any molecular cloud, thermal energy works to keep particles moving, bouncing off one another, resisting compression. This outward pressure is directly related to temperature. Even at the frigid temperatures of 10 to 20 Kelvin found in these clouds, gas particles still possess kinetic energy. They vibrate, they drift, they collide. This motion creates pressure that pushes outward against any force attempting to squeeze the gas together. Working against this thermal pressure is gravity. Every particle of matter attracts every other particle, and in a sufficiently dense region, this collective gravitational pull can overwhelm the outward thermal pressure. The Jeans mass represents the precise amount of material needed for gravity to win this contest. Below this threshold, thermal pressure maintains stability. Above it, collapse becomes inevitable. The mathematics reveal something elegant. The Jeans mass depends on only two properties of the cloud: its temperature and its density. For a typical molecular cloud with a temperature of 10 Kelvin and a density of roughly 1,000 hydrogen molecules per cubic centimeter, the Jeans mass works out to approximately 1 to 2 solar masses. This means that any clump of gas exceeding this mass will begin to contract under its own gravity. But the calculation contains a subtlety that shapes the entire process of star formation. As a region begins to collapse, its density increases, and as density increases, the Jeans mass decreases. A collapsing cloud fragment that started with 10 solar masses will, as it contracts, find that smaller and smaller subregions within it now exceed their local Jeans mass. These subregions begin their own independent collapses. The original fragment breaks apart, fragmenting into multiple smaller cores, each destined to become a separate star. This fragmentation process explains why stars rarely form in isolation. The giant molecular clouds that spawn stellar nurseries typically contain enough mass for thousands or tens of thousands of stars. As collapse proceeds, the cloud breaks into clusters, groups, and associations of young stars all born from the same parent material. The Orion Nebula, visible to the naked eye as a fuzzy patch in the sword of the constellation Orion, contains over 3,000 young stars that formed together from a single massive cloud complex. The initial trigger for collapse can take many forms. A passing shock wave from a nearby supernova can compress a previously stable region, pushing its density above the critical threshold. The the spiral density waves that create the arms of galaxies like the Milky Way sweep through the interstellar medium, piling up gas and dust like traffic slowing on a highway. Collisions between clouds, turbulent eddies within the gas, even the radiation pressure from nearby hot stars can all initiate the process. Once collapse begins, it proceeds through distinct phases. The earliest stage is called free-fall collapse, and it happens remarkably quickly by astronomical standards. A cloud core with a density of 10,000 particles per cubic centimeter will collapse to its center in roughly 400,000 years. This timescale depends only on density, not on mass, which means that all parts of a uniform cloud would collapse simultaneously if the cloud were perfectly homogeneous. Real clouds are not homogeneous. They contain density variations, turbulent motions, magnetic fields threading through the gas, and rotation inherited from the larger cloud complex. These factors complicate the simple picture of spherical freefall, but do not prevent collapse. They shape it, channel it, slow it in some regions while accelerating it in others. Magnetic fields deserve particular attention. The gas in molecular clouds is not electrically neutral. A small fraction of atoms and molecules carry electric charges, ionized by cosmic rays that penetrate even the densest cloud cores. These charged particles are tied to magnetic field lines, and as they move, they drag the neutral gas along with them through collisions. The magnetic field acts as a kind of scaffolding, providing support against gravity and channeling the flow of collapsing material. In regions where magnetic fields are strong, collapse proceeds preferentially along the field lines rather than across them. The gas flows like beads sliding down wires, funneling toward the densest points where field lines converge. This process, called ambipolar diffusion, allows neutral particles to slowly drift through the magnetic scaffolding, gradually concentrating mass at the center of the collapsing core. The timescale for ambipolar diffusion is longer than pure free fall, stretching the collapse phase to 1 or 2 million years in strongly magnetized regions. As the central density increases, something important changes in the physics of the collapse. At low densities, the cloud is optically thin, meaning that thermal radiation from the gas can escape freely into space. Any heat generated by compression radiates away, keeping the temperature nearly constant. This isothermal phase allows collapse to proceed efficiently because the thermal pressure does not increase even as density rises. But when the central density reaches approximately 10 billion particles per cubic centimeter, the gas becomes optically thick. Radiation can no longer escape. Heat generated by compression becomes trapped, and the temperature begins to rise. This transition marks the formation of what astronomers call the first hydrostatic core, a small, hot, dense object at the center of the collapsing cloud that has temporarily halted its contraction. The first hydrostatic core is not yet a star. It is a transient structure, typically containing only about 1% of a solar mass and spanning roughly 5 astronomical units in diameter, about the distance from the Sun to Jupiter. Its central temperature reaches perhaps 100 to 200 Kelvin, warm compared to the surrounding cloud, but far below the millions of degrees needed for nuclear fusion. This core continues to grow as material from the surrounding envelope rains down upon it. The infalling gas strikes the surface at velocities of several kilometers per second, creating an accretion shock where kinetic energy converts to thermal energy. The luminosity of this accretion process can exceed the luminosity of the Sun, even though no nuclear reactions have yet begun. This energy comes purely from gravity, from the conversion of gravitational potential energy into heat as matter falls inward. As mass accumulates and the central temperature rises, the first hydrostatic core eventually reaches approximately 2000 Kelvin. At this temperature, hydrogen molecules begin to dissociate, breaking apart into individual hydrogen atoms. This dissociation absorbs enormous amounts of energy, roughly 4.5 electron volts per molecule, and the core can no longer maintain hydrostatic equilibrium. A second phase of collapse begins, even more rapid than the first. This second collapse is violent and brief, lasting only a few years. The central region contracts from several astronomical units to less than a solar radius, increasing in density by more than 10 orders of magnitude. When the collapse finally halts, a true protostar has formed, a dense, hot object that will eventually ignite hydrogen fusion in its core. The central temperature now exceeds 100,000 Kelvin, and the object has begun its long journey toward the main sequence. The physics of gravitational collapse thus transforms cold, diffuse gas into concentrated hot matter through a cascade of instabilities and equilibria. Each stage prepares the conditions for the next. The gene's mass sets the initial threshold. Fragmentation determines how many stars will form. Magnetic fields and rotation shape the geometry of infall, and the transition from isothermal to adiabatic collapse marks the birth of a distinct object that will carry forward the process of stellar evolution. The dense core that emerges from gravitational collapse does not sit in isolation. It remains connected to its parent cloud by streams of infalling material, and the geometry of this accretion determines much of what the protostar will become. Angular momentum, conserved from the original turbulent motions of the molecular cloud, prevents matter from falling directly onto the central object. Instead, the gas spirals inward, spreading into a flattened structure that astronomers call a circumstellar disk or protoplanetary disk. The formation of this disk follows directly from the laws of rotating systems. Consider a parcel of gas falling towards the protostar from a distance of several thousand astronomical units. If this gas carries even a small amount of rotational motion, perhaps inherited from the slow spin of the original cloud fragment, it cannot simply plunge straight down. Conservation of angular momentum requires that as the parcel moves closer to the center, its rotational velocity must increase. At some point, the centrifugal acceleration balances the gravitational pull, and the gas settles into a circular orbit rather than continuing its inward fall. This radius, where rotation halts the collapse, is called the centrifugal radius, and it typically lies between 50 and several hundred astronomical units from the protostar. Gas arriving from different directions, carrying slightly different amounts of angular momentum, settles at different radii. The result is a disk that extends from very close to the protostar, perhaps within a fraction of an astronomical unit, out to several hundred astronomical units or more. The disk is not uniform. Its density decreases with distance from the center, following a power law that observations suggest scales roughly as the radius to the -3/2 power. Near the protostar, the disk may contain several grams of material per cubic centimeter. At its outer edges, the density drops to a few 100,000 molecules per cubic centimeter, still far denser than the interstellar medium, but thin by terrestrial standards. The temperature structure of the disk also varies dramatically with location. Close to the protostar, where the central object radiates intensely and where gravitational energy release heats the infalling material, temperatures can exceed 1500 Kelvin. At these temperatures, even refractory materials like silicates and iron compounds exist as vapor. Moving outward, the temperature drops steadily. At 1 astronomical unit, roughly the distance from the Sun to Earth, disk temperatures typically range from 200 to 400 Kelvin. Beyond 5 astronomical units, temperatures fall below 170 Kelvin, cold enough for water ice to condense. This boundary, called the snow line or ice line, plays a crucial role in determining what kinds of planets might eventually form from the disk material. The disk does not simply sit there, passively orbiting the protostar. It is a dynamic, evolving structure through which mass flows steadily inward, while angular momentum flows outward. This transport occurs through a process called viscous accretion, though the word viscous here does not refer to the ordinary molecular viscosity of gases, which would be far too weak to matter on these scales. Instead, the effective viscosity arises from turbulence within the disk, turbulence that may be driven by magnetic fields threading through the partially ionized gas. The most widely studied mechanism for this turbulence is the magnetorotational instability, often abbreviated as MRI, in a disk where the gas is weakly magnetized and where the orbital velocity decreases with distance from the center, as it does in any Keplerian disk. Small perturbations in the magnetic field can grow exponentially. The instability works because magnetic field lines connect gas parcels at different radii. When a parcel at an inner radius, orbiting faster, is connected by a field line to a parcel at an outer radius, orbiting slower, the field line acts like a spring. It transfers angular momentum from the inner parcel to the outer one, causing the inner parcel to slow down and fall further inward, while the outer parcel speeds up and moves outward. This exchange amplifies the initial perturbation, driving vigorous turbulence that transports angular momentum outward through the disk. The rate at which mass flows through the disk onto the protostar depends on the strength of this turbulent viscosity. Observations of young stellar objects suggest accretion rates that vary widely, from as low as 10 to the -9 solar masses per year in older, more evolved disks, to as high as 10 to the -5 solar masses per year during violent outburst phases. A typical value for a young protostar might be 10 to the -7 solar masses per year, meaning that over 1 million years, the protostar could accumulate a tenth of a solar mass from its disk. The accretion process releases enormous amounts of energy. As gas falls from the outer disk towards the protostar, it converts gravitational potential energy into kinetic energy and then into heat as turbulent motions dissipate. Half of this energy radiates away from the disk surfaces, while the other half is carried inward with the accreting gas and eventually released when the material strikes the protostar, For a solar mass protostar accreting at 10 to the negative 7 solar masses per year, the total accretion luminosity can reach several solar luminosities, far exceeding the energy that the protostar generates through gravitational contraction alone. This accretion luminosity makes young protostars surprisingly bright for their mass. A protostar that will eventually become a sun-like star may shine with 10 or even 100 times the luminosity of the present-day sun during its most active accretion phase. Much of this radiation emerges at infrared wavelengths because the surrounding disk and envelope of dust absorb the shorter wavelength light and re-emit it at longer wavelengths. This is why protostars are best studied with infrared telescopes, which can peer through the obscuring dust to see the warm glow of the accreting system. The disk does not feed the protostar smoothly. Observations reveal that accretion is episodic, punctuated by dramatic outbursts during which the accretion rate increases by factors of 100 or more. These outbursts, known as FU Orionis events after the prototype star FU Orionis, can cause a young stellar object to brighten by 5 magnitudes or more over the course of just a few years. The outburst then fades slowly over decades or centuries as the disk returns to a quiescent state. The cause of these outbursts remains debated, but likely involves instabilities in the inner disk, perhaps triggered by the accumulation of material that suddenly releases when some threshold is crossed. Not all the infalling material reaches the protostar. A significant fraction is ejected back into space through powerful bipolar outflows that emerge perpendicular to the disk plane. These outflows appear to be launched from the inner regions of the disk, within a few stellar radii of the protostar, where magnetic field lines anchored in the rotating disk are twisted and wound up by the differential rotation. The magnetic pressure in these wound-up field lines accelerates gas outward along the rotation axis, producing jets that can travel at speeds of 100 to several hundred kilometers per second. These jets carry away not only mass, but also angular momentum, helping to solve a fundamental problem in star formation. If all the angular momentum of the infalling material were deposited onto the protostar, the star would spin so fast that centrifugal forces would tear it apart. The jets provide an escape valve, removing angular momentum from the system and allowing the protostar to accrete mass without spinning up to destruction. Observations suggest that for every unit of mass that falls onto the protostar, perhaps 1/10 of a unit is ejected in the outflow, carrying away a disproportionate share of the angular momentum. The jets interact violently with the surrounding molecular cloud, sweeping up ambient gas and creating shock waves that heat the material to thousands of Kelvin. These shocks produce the glowing knots and bow-shaped structures known as Herbig-Haro objects, named after the astronomers George Herbig and Guillermo Haro, who first studied them systematically. The Herbig-Haro objects trace the history of the jet, with each knot representing a past episode of enhanced ejection. By measuring the spacing and velocities of these knots, astronomers can reconstruct the outburst history of the protostar over thousands of years. As the protostar continues to accumulate mass from its surrounding envelope, the conditions at its center grow steadily more extreme. The gravitational compression that began in the cold molecular cloud now drives temperatures and pressures toward thresholds that will fundamentally transform the nature of matter itself. The core, once a frigid clump at 10 Kelvin, has already climbed past 100,000 Kelvin, then past 1 million. Each doubling of temperature represents another step toward the critical boundary where hydrogen nuclei will begin to fuse. The journey to ignition is not instantaneous. For a protostar of roughly 1 solar mass, the contraction phase lasts approximately 50 million years. During this time, the object slowly shrinks, converting gravitational potential energy into thermal energy according to the virial theorem. This fundamental principle of physics states that for a self-gravitating system in equilibrium, half of the released gravitational energy heats the interior, while the other half radiates away into space. The protostar glows not from nuclear reactions, but from the slow squeeze of gravity, shining with a luminosity that can exceed the sun's current output, even though no fusion has yet begun. The internal structure of the protostar during this phase is fully convective. Hot gas from the center rises toward the surface, cools by radiating energy into space, and sinks back down in a continuous churning motion. This convection efficiently transports heat outward and keeps the chemical composition uniform throughout the interior. The mixing ensures that fresh hydrogen is constantly cycled through the core, preparing the fuel supply for the fusion reactions to come. As the central temperature approaches 3 million Kelvin, the first nuclear reactions begin to occur, though they are not yet the primary hydrogen fusion that will define the star's main sequence life. Instead, trace amounts of deuterium, a heavy isotope of hydrogen containing 1 proton and 1 neutron, begin to fuse with ordinary hydrogen nuclei. Deuterium fusion occurs at lower temperatures than ordinary hydrogen fusion because the reaction does not require the creation of a new particle. The deuterium nucleus already contains the neutron that would otherwise need to be produced through the weak nuclear force. This deuterium burning phase provides a temporary energy source that slows the protostar's contraction. The primordial abundance of deuterium in the universe, set during the first few minutes after the Big Bang, is approximately 25 parts per million relative to hydrogen. Though this seems minuscule, the energy released by fusing this trace deuterium is significant enough to stabilize the protostar for a brief period, typically lasting a few million years. The object hovers at a nearly constant radius, its luminosity sustained by deuterium fusion rather than gravitational contraction. But the deuterium supply is finite and quickly exhausted. Once the trace deuterium has been consumed, the protostar resumes its contraction and the central temperature continues to climb. At 5 million Kelvin, the thermal energy of the hydrogen nuclei becomes substantial, but still insufficient to overcome the electromagnetic repulsion between protons. The Coulomb barrier, the electrostatic force that pushes positively charged particles apart, stands as a formidable obstacle. 2 protons approaching each other experience a repulsive force that increases as they draw closer, creating an energy barrier that classical physics would deem insurmountable at these temperatures. The resolution to this apparent paradox lies in quantum mechanics. At the scales of atomic nuclei, particles do not behave as solid spheres following deterministic paths. Instead, they exist as probability waves, their positions and momenta described by wave functions that spread across space. This wave nature allows for a phenomenon called quantum tunneling, where a particle has a finite probability of appearing on the other side of an energy barrier, even if it lacks the classical energy to climb over it. The probability of tunneling depends exponentially on the height and width of the barrier, which in turn depends on the relative velocity of the approaching nuclei. At 10 million Kelvin, the core of the protostar finally reaches the threshold, where quantum tunneling becomes efficient enough to sustain continuous hydrogen fusion. The thermal velocities of the protons, distributed according to the Maxwell-Boltzmann distribution, ensure that a small fraction of particles move fast enough to have appreciable tunneling probabilities. It is not the average particle that fuses, but rather those in the high-velocity tail of the distribution, the fastest few percent that carry enough kinetic energy to approach their neighbors closely. The first reaction in the proton-proton chain begins when two hydrogen nuclei, simple protons, tunnel through the Coulomb barrier and approach within approximately 1 femtometer of each other, close enough for the strong nuclear force to take hold. But even at this intimate distance, fusion is not guaranteed. The strong force binds protons and neutrons together, but two protons alone cannot form a stable nucleus. The diproton, if it existed, would immediately fly apart. For fusion to proceed, one of the protons must transform into a neutron through the weak nuclear force, emitting a positron and an electron neutrino in the process. This requirement for a weak interaction makes the first step of the proton-proton chain extraordinarily slow. The weak nuclear force operates at timescales billions of times longer than the strong force. On average, a proton in the solar core will wait approximately 9 billion years before successfully fusing with another proton. This staggering timescale is what allows stars to burn steadily for billions of years, rather than exploding in a flash. The weak interaction acts as a bottleneck, metering out the energy release at a rate that gravity can comfortably balance. When the rare fusion event does occur, the product is a deuterium nucleus containing 1 proton and 1 neutron bound together. The positron emitted in the reaction immediately encounters one of the abundant electrons in the plasma and annihilates, converting the combined mass of the electron-positron pair into 2 gamma-ray photons, carrying 1.022 million electron volts of energy. The neutrino, meanwhile, escapes the star entirely, passing through the overlying mass as if it were empty space. Neutrinos interact so weakly with matter that they travel from the core to the surface in approximately 2 seconds, while the energy carried by photons will take hundreds of thousands of years to make the same journey. The deuterium nucleus produced in the first reaction does not linger. Within approximately 1 second, it captures another proton to form helium-3, a light isotope of helium containing 2 protons and 1 neutron. This reaction proceeds through the strong force alone and releases a gamma ray carrying 5.49 million electron volts. The helium-3 nucleus is stable, but represents only an intermediate step in the chain. The final stage of the proton-proton chain occurs when 2 helium-3 nuclei collide and fuse, producing 1 helium-4 nucleus and releasing 2 protons back into the plasma. This reaction completes the cycle, having converted 4 hydrogen nuclei into 1 helium nucleus, while releasing energy in the form of gamma rays, positrons, and neutrinos. The mass of the final helium-4 nucleus is slightly less than the combined mass of the 4 original protons, with the difference of 0.7% converted into energy, according to Einstein's famous equation relating mass and energy. The moment when these reactions become self-sustaining marks the birth of a true star. The energy released in the core creates an outward pressure that halts the gravitational contraction. The star settles into a hydrostatic equilibrium, a state where the inward pull of gravity at every layer is precisely balanced by the outward push of pressure from the hot gas below. This balance is not static but dynamic, maintained by a feedback loop of exquisite sensitivity. If the core contracts slightly, the temperature rises, fusion rates increase, more energy is released, pressure builds, and the core expands back to its equilibrium size. If the core expands, the temperature drops, fusion slows, pressure decreases, and gravity pulls the core back inward. For a star of 1 solar mass, the core temperature at the onset of stable hydrogen fusion is approximately 15 million Kelvin. The density at the center reaches about 150 grams per cubic centimeter, roughly 15 times the density of lead. Yet the matter remains in a gaseous state, because the thermal energy of the particles prevents them from condensing into a solid or liquid. The pressure at the core is approximately 250 billion atmospheres, a value so extreme that it compresses the hydrogen plasma to conditions found nowhere else in the solar system. This balance, once achieved, defines the fundamental nature of a star. It is called hydrostatic equilibrium, and it represents one of the most elegant physical states in the universe. Every point within the stellar interior exists in a condition where the inward pull of gravity is precisely counteracted by the outward push of pressure. Not approximately balanced, not nearly equal, but exactly matched, down to the finest measurable degree. To understand this equilibrium, consider the forces acting on a small parcel of gas located somewhere within the star's interior. Above this parcel lies an enormous column of stellar material pressing downward with tremendous weight. The gravitational attraction of all the mass below the parcel pulls it toward the center. Together, these forces create an inward pressure that would, in the absence of any opposing force, cause the parcel to accelerate towards the core at thousands of meters per second squared. Yet the parcel does not fall. It remains suspended at its position within the star, because the gas below it exerts an upward pressure. This pressure arises from the thermal motion of particles, the kinetic energy of hydrogen nuclei, helium nuclei, and free electrons moving at velocities of hundreds of kilometers per second. The hotter and denser the gas, the greater the pressure it exerts. At every depth within the star, the pressure gradient, the rate at which pressure increases with depth, exactly compensates for the gravitational force. The mathematical expression of this balance is deceptively simple. The change in pressure with respect to radius equals the negative product of the local density, the gravitational constant, and the mass enclosed within that radius, divided by the radius squared. This differential equation, combined with equations describing how mass, temperature and energy generation vary with radius, forms the foundation of stellar structure theory. From these equations, astronomers can predict the internal conditions of stars they will never directly observe. For the Sun, this equilibrium produces a pressure profile that varies by a factor of more than 200 billion from the core to the surface. At the center, the pressure reaches approximately 2.5 times 10 to the 16th power pascals, or about 250 billion times the atmospheric pressure at Earth's surface. At the photosphere, the visible surface of the Sun, the pressure drops to roughly 0.01 pascals, a value lower than the best laboratory vacuums achievable on Earth. This enormous gradient exists in a state of perfect mechanical balance. The temperature profile follows a similar pattern. The core temperature of 15 million Kelvin drops steadily through the radiative zone, where energy transport occurs through the absorption and re-emission of photons. By the time the stellar material reaches the base of the convective zone, approximately 70% of the way from the center to the surface, the temperature has fallen to about 2 million Kelvin. Through the convective zone, where energy is carried by rising and falling currents of plasma, the temperature continues to decrease until it reaches approximately 5,778 Kelvin at the photosphere. The density gradient is equally dramatic. The core density of 150 grams per cubic centimeter, roughly 15 times that of lead, decreases through the interior until it reaches values of approximately 10 to the negative 7th grams per cubic centimeter at the photosphere, thinner than the air at the top of Earth's atmosphere. Despite this variation spanning more than 10 orders of magnitude, the star maintains its equilibrium configuration with remarkable stability. This stability arises from a self-regulating feedback mechanism that operates on timescales of minutes to hours. If some perturbation were to compress the core slightly, the increased density would raise the temperature, which would increase the rate of nuclear fusion. The additional energy released would create more pressure, pushing the core back outward. Conversely, if the core were to expand slightly, the decreased density would lower the temperature, reducing the fusion rate. With less energy being generated, the pressure would drop, and gravity would pull the core back inward. The timescale on which this regulation operates is called the Kelvin-Helmholtz timescale, named after the physicists Lord Kelvin and Hermann von Helmholtz, who first calculated it in the 19th century. For the Sun, this timescale is approximately 30 million years, representing the time it would take for the star to radiate away all its gravitational potential energy if nuclear fusion were to cease. On shorter timescales, the star responds to perturbations through pressure waves that travel through the interior at the local sound speed, which reaches approximately 500 kilometers per second in the solar core. The existence of hydrostatic equilibrium explains why stars are spherical. Gravity pulls equally in all directions toward the center of mass, and pressure pushes equally in all directions away from any point of high density. The only shape that satisfies these conditions simultaneously at every point is a sphere. Deviations from perfect sphericity occur only when other forces are present, such as the centrifugal force from rapid rotation, which causes some stars to bulge at their equators. For a star rotating as slowly as the Sun, which completes one rotation approximately every 25 days at its equator, the deviation from sphericity is negligible. The solar equatorial radius exceeds the polar radius by only about 10 kilometers out of a total radius of 696,000 kilometers, a difference of less than 0.002%. For rapidly rotating stars, however, the equatorial bulge can become significant. The star Achernar, which rotates with an equatorial velocity of approximately 250 kilometers per second, has an equatorial radius roughly 50% larger than its polar radius. The condition of hydrostatic equilibrium also determines the relationship between a star's mass and its other properties. More massive stars must generate more pressure to support their greater weight, which requires higher core temperatures. Higher temperatures produce more rapid nuclear fusion, which generates more luminosity. This chain of reasoning leads to the mass-luminosity relation, one of the most important empirical relationships in stellar astrophysics. For main sequence stars, the luminosity scales approximately as the mass raised to the power of 3.5. A star twice as massive as the Sun is not twice as luminous, but roughly 11 times as luminous. A star 10 times as massive as the Sun is approximately 3,000 times as luminous. This steep dependence of luminosity on mass has profound consequences for stellar lifetimes, as more luminous stars consume their nuclear fuel far more rapidly. The central temperature required to maintain hydrostatic equilibrium also scales with mass. While the Sun's core reaches 15 million Kelvin, a star of 10 solar masses requires a core temperature of approximately 40 million Kelvin to generate sufficient pressure. At these higher temperatures, different nuclear reaction pathways become dominant, fundamentally altering the internal structure and evolution of the star. The equilibrium state is not static, but represents a slow, continuous adjustment as the star's composition changes through nuclear fusion. Each second, the Sun converts approximately 600 million tons of hydrogen into 596 million tons of helium, with the missing 4 million tons transformed into energy according to Einstein's mass-energy equivalence. This gradual conversion of hydrogen to helium changes the mean molecular weight of the core material, which affects the pressure and requires subtle adjustments to the temperature and density profiles. Over billions of years, these adjustments accumulate. The Sun today is approximately 30% more luminous than it was 4.6 billion years ago when it first reached the main sequence. Its core has contracted slightly and heated, while its outer layers have expanded. These changes are imperceptibly slow on human timescales, but they represent the inevitable evolution of a star in hydrostatic equilibrium, burning through its finite supply of nuclear fuel. The balance persists moment by moment as gravity and pressure negotiate their endless compromise. Neither force dominates, neither force yields. In this equilibrium, the star finds its identity, its luminosity, its temperature, its size. The physics is precise, the mathematics exact, and the result is a sphere of plasma that will shine steadily for billions of years, its light carrying across the void to illuminate distant worlds. The light that emerges from a star like the Sun carries with it a story written in nuclear physics, a tale of transformation that begins in the crushing density of the stellar core. At the center of our nearest star, where temperatures reach 15 million Kelvin and pressures exceed 250 billion atmospheres, hydrogen nuclei undergo a series of reactions that convert mass into energy, with an efficiency that powers the entire solar system. This process, known as the proton-proton chain, is the dominant energy source for stars with masses similar to or less than the Sun. It proceeds through a sequence of steps, each governed by the fundamental forces of nature, each contributing to the steady luminosity that has bathed Earth for over 4 billion years. The chain begins with the simplest possible fusion reaction, the collision of two protons, and ends with the creation of helium, the second element on the periodic table. To understand why this process works, one must first appreciate the challenge it overcomes. Two protons, each carrying a positive electrical charge, experience a powerful repulsive force as they approach each other. This Coulomb barrier, as physicists call it, would seem to make fusion impossible at the temperatures found in stellar cores. At 15 million Kelvin, the average proton moves at approximately 500 kilometers per second, carrying kinetic energy of roughly 2,000 electron volts. Yet the Coulomb barrier between two protons requires nearly 1 million electron volts to overcome through classical means. The resolution to this apparent paradox lies in quantum mechanics, specifically in a phenomenon called quantum tunneling. At the subatomic scale, particles do not behave as solid objects with definite positions. Instead, they exist as probability waves, their locations described by mathematical functions that spread across space. When two protons approach each other, there exists a small but non-zero probability that they will find themselves on the other side of the Coulomb barrier, close enough for the strong nuclear force to take hold. This tunneling probability is extraordinarily small. For any given pair of protons in the solar core, the chance of successful fusion is roughly 1 in 10 to the 28th power per second. This number is so vanishingly tiny that if only a handful of protons existed, fusion would never occur within the lifetime of the universe. But the Sun's core contains approximately 10 to the 57th protons, and at any moment, countless collisions are occurring. Statistics and patience combine to produce a steady rate of fusion, roughly 3.8 times 10 to the 38th protons fusing every second. The first step of the proton-proton chain involves two protons colliding and fusing to form a nucleus of deuterium, also known as heavy hydrogen. This reaction is the slowest in the entire chain, the bottleneck that determines the overall rate of energy production. During the collision, one of the protons must undergo a transformation, converting into a neutron through the weak nuclear force. This process releases a positron, the antimatter counterpart of an electron, and a neutrino, a nearly massless particle that interacts so weakly with matter that it escapes the Sun within seconds. The positron immediately encounters one of the countless electrons in the solar plasma. Matter and antimatter annihilate upon contact, converting their combined mass into two gamma-ray photons with energies of 511,000 electron volts each. These photons begin their long journey outward, a migration that will take hundreds of thousands of years as they scatter repeatedly off the dense plasma. The neutrino, meanwhile, passes through the Sun as if it were not there. Traveling at nearly the speed of light, it reaches the solar surface in just over 2 seconds and continues into space. Approximately 65 billion solar neutrinos pass through every square centimeter of Earth's surface every second, yet almost none interact with the matter they encounter. Detecting these ghostly particles requires enormous underground detectors filled with thousands of tons of water or other materials, waiting for the rare occasions when a neutrino happens to strike an atomic nucleus. The deuterium nucleus produced as the first step does not remain alone for long. Within approximately 1 second, it collides with another proton, fusing to form helium-3, an isotope of helium containing 2 protons and 1 neutron. This reaction releases a gamma-ray photon with an energy of 5.5 million electron volts, adding to the radiation slowly diffusing outward through the star. The final step of the most common proton-proton chain pathway, designated PP1, involves 2 helium-3 nuclei colliding and fusing. This reaction produces a nucleus of helium-4, the stable isotope with 2 protons and 2 neutrons, while releasing 2 protons back into the plasma. These liberated protons are free to participate in new fusion reactions, continuing the cycle. The net result of the complete PP1 chain is the conversion of 4 hydrogen nuclei into 1 helium nucleus, with the release of 2 positrons, 2 neutrinos, and several gamma-ray photons. The mass of 4 protons is 4.031 atomic mass units, while the mass of 1 helium-4 nucleus is 4.003 atomic mass units. The difference, 0.028 atomic mass units, has been converted into energy, according to Einstein's famous equation relating mass and energy. This mass deficit translates to 26.7 million electron volts of energy released per completed chain. Approximately 2% of this energy escapes immediately in the form of neutrinos, carrying away roughly 500,000 electron volts that will never contribute to the star's luminosity. The remaining energy heats the core and eventually radiates into space as the light we see. At temperatures above 15 million Kelvin, alternative pathways become significant. The PP2 chain occurs when helium-3 captures an existing helium-4 nucleus instead of fusing with another helium-3. This produces beryllium-7, an unstable isotope that captures an electron and decays into lithium-7, releasing a neutrino with higher energy than those from the PPI chain. The lithium-7 then captures a proton and splits into 2 helium-4 nuclei. The PP3 chain, even rarer, involves beryllium-7 capturing a proton to form boron-8, which rapidly decays into beryllium-8 while emitting a positron and a high-energy neutrino. The beryllium-8 immediately splits into 2 helium-4 nuclei. Though this pathway accounts for only about 0.02% of solar energy production, the neutrinos it produces are energetic enough to be detected more easily, making them valuable probes of conditions in the solar core. The rate at which the proton-proton chain proceeds depends sensitively on temperature. The fusion rate scales approximately as the 4th power of temperature in the solar core, meaning that a 10% increase in temperature would increase energy production by nearly 50%. This sensitivity creates a natural thermostat within the star. If the core were to heat slightly, fusion would accelerate, increasing radiation pressure and causing the core to expand. The expansion would lower the density and temperature, reducing the fusion rate back toward equilibrium. In the Sun, the proton-proton chain converts approximately 600 million tons of hydrogen into helium every second. Of this mass, 4.3 million tons are transformed directly into energy, primarily in the form of gamma-ray photons. This rate has remained relatively constant for billions of years, sustained by the vast reservoir of hydrogen in the solar core. The helium produced by fusion accumulates gradually at the center of the star, where temperatures and pressures are highest. Over billions of years, this helium ash builds up, slowly changing the composition of the core. Fresh hydrogen continues to fuse in a shell surrounding the growing helium center, but the core itself becomes increasingly inert, unable to fuse helium at the temperatures that sustain hydrogen burning. This accumulation has consequences that will unfold over cosmic timescales. As helium replaces hydrogen in the core, the mean molecular weight of the gas increases. To maintain the pressure needed to support the overlying layers, the core must contract and heat. The fusion rate in the surrounding hydrogen shell increases, and the star gradually brightens. The Sun today is approximately 30% more luminous than it was when it first reached the main sequence, a slow brightening that will continue for billions of years to come. The proton-proton chain is a patient process, converting matter into light one reaction at a time, each fusion event contributing its small share to the star's radiance. The physics is quantum mechanical, the timescales astronomical, and the result is the steady glow of a main sequence star, burning through its hydrogen fuel with the measured pace of a candle that will last for 10 billion years. For stars more massive than the Sun, the proton-proton chain is not the dominant pathway of energy generation. The physics remains the same. 4 hydrogen nuclei must ultimately fuse into one helium nucleus, but the route taken through this transformation differs dramatically. In stellar cores that exceed 15 million Kelvin, a different mechanism takes over, one that uses carbon, nitrogen, and oxygen as catalysts to accelerate the fusion process. This is the CNO cycle, and it powers the most luminous stars in the universe. The distinction arises from temperature sensitivity. The proton-proton chain increases its reaction rate relatively gently as temperature rises, scaling roughly as the 4th power of temperature. The CNO cycle, by contrast, scales as the 16th power of temperature. This extreme sensitivity means that even modest increases in core temperature produce enormous increases in energy output. At 15 million Kelvin, the two processes contribute roughly equally to a star's luminosity. Above this threshold, the CNO cycle rapidly dominates, and by the time core temperatures reach 20 million Kelvin, it accounts for the vast majority of fusion energy. The cycle begins with the carbon-12 nucleus, one of the most stable configurations of protons and neutrons in nature. This carbon nucleus captures a proton, forming nitrogen-13. The reaction releases a gamma-ray photon, carrying away some of the binding energy difference between the initial and final states. Nitrogen-13 is unstable, with a half-life of approximately 10 minutes. It undergoes beta-plus decay, emitting a positron and a neutrino. and transforms into carbon-13. Carbon-13 then captures another proton, becoming nitrogen-14 and releasing another gamma ray. Nitrogen-14 is stable and represents the slowest step in the entire cycle. The capture of a proton by nitrogen-14 to form oxygen-15 has the lowest probability of all the reactions in the chain, making it the bottleneck that determines the overall rate. This is why nitrogen-14 accumulates in the cores of massive stars, building up as the cycle processes hydrogen into helium. Oxygen-15, once formed, is highly unstable. With a half-life of just over 2 minutes, it decays via beta-plus emission into nitrogen-15, releasing another positron and neutrino. The nitrogen-15 nucleus then captures a final proton, but instead of forming oxygen-16, the nucleus splits apart. It ejects an alpha particle, a helium-4 nucleus, and returns to carbon-12. The cycle is complete. The carbon catalyst has been restored, ready to process another set of 4 protons into helium. The net result is identical to the proton-proton chain. 4 hydrogen nuclei have been converted into 1 helium nucleus, 2 positrons, 2 neutrinos, and gamma-ray photons carrying approximately 26.7 million electron volts of energy. The carbon, nitrogen, and oxygen nuclei are neither created nor destroyed in the overall process. They serve purely as intermediaries, facilitating the fusion without being consumed. The temperature sensitivity of the CNO cycle has profound consequences for stellar structure. In a star like the Sun, energy generation is distributed throughout a substantial fraction of the core, with the reaction rate declining gradually as temperature drops with distance from the center. The energy transport is relatively gentle, and radiation can carry the heat outward through a radiative zone that extends through much of the stellar interior. In massive stars, the situation is dramatically different. The 16th power temperature dependence concentrates energy generation into a tiny central region. A star of 10 solar masses might generate nearly all its nuclear energy within a core just a few % of its total radius. This concentrated energy release creates a steep temperature gradient that radiation alone cannot efficiently transport. The result is convection, the physical churning of stellar material as hot plasma rises and cooler plasma sinks. The convective core of a massive star acts like a boiling pot, constantly mixing fresh hydrogen fuel into the fusion region and carrying helium ash outward. This mixing has important consequences for stellar evolution. It allows massive stars to burn a larger fraction of their total hydrogen supply than the Sun can access, because fuel from outer regions is continuously transported into the burning zone. A star of 15 solar masses might convert nearly 10% of its total mass into helium before exhausting its core hydrogen supply. The convective motions also homogenize the chemical composition of the core. While the Sun's core gradually develops a helium-rich center surrounded by hydrogen-rich layers, a massive star's convective core maintains a uniform mixture throughout. The boundary between the convective core and the overlying radiative envelope is sharp, defined by the point where the temperature gradient becomes shallow enough for radiation to carry the energy flux. The luminosity of CNO cycle stars is extraordinary. A star of 10 solar masses shines with approximately 10,000 times the Sun's luminosity. A star of 50 solar masses might exceed 1,000,000 solar luminosities. This prodigious energy output comes at a cost measured in stellar lifetimes. While the Sun will spend 10 billion years on the main sequence, a 10 solar mass star exhausts its core hydrogen in roughly 20 million years. A 50 solar mass star might burn through its fuel in just 3 million years, a cosmic eye blink. The neutrinos produced by the CNO cycle carry away approximately the same fraction of energy as those from the proton-proton chain, roughly 2% of the total. But the absolute neutrino luminosity of massive stars is far greater, proportional to their enormous fusion rates. These neutrinos stream outward at nearly the speed of light, passing through the stellar material as if it were transparent, carrying information about the nuclear processes occurring in the hidden core. The positrons produced in the beta decays immediately encounter electrons in the dense plasma and annihilate, converting their combined mass into gamma-ray photons. Each annihilation releases 1.022 million electron volts, adding to the energy that must eventually work its way to the stellar surface. The gamma rays from both the fusion reactions and the positron annihilations begin their long journey outward, scattering countless times through the stellar interior. There exists a secondary branch of the CNO cycle that becomes important at even higher temperatures. When core temperatures exceed approximately 25 million Kelvin, some of the nitrogen-15 nuclei capture protons to form oxygen-16 instead of ejecting alpha particles. This opens a second loop involving oxygen-16, oxygen-17, and fluorine isotopes, ultimately returning to nitrogen-14 and continuing the cycle. At the highest temperatures found in the most massive stars, these secondary branches contribute significantly to the overall energy generation. The presence of carbon, nitrogen, and oxygen in stellar cores is itself a legacy of previous stellar generations. The primordial universe, emerging from the Big Bang, contained only hydrogen, helium, and trace amounts of lithium. The first stars formed from this pristine material had no CNO nuclei to catalyze fusion. They relied entirely on the proton-proton chain, regardless of their mass and core temperature. These population 3 stars, as astronomers call them, had structures quite different from the massive stars we observe today. Modern massive stars inherit their CNO nuclei from the interstellar medium, enriched by billions of years of stellar nucleosyntheses and supernova explosions. Even a tiny abundance of these elements, less than 1% by mass, is sufficient to enable the CNO cycle. The cycle's efficiency depends on having enough catalyst nuclei to process the available protons, but the required abundance is remarkably small. The steep temperature gradient in CNO cycle cores creates conditions favorable for various instabilities. The boundary between the convective core and the radiative envelope can develop mixing processes that transport material across this interface, a phenomenon called convective overshooting. The extent of this overshooting affects how much fuel the star can ultimately access and influences the star's evolutionary track across the Hertzsprung-Russell diagram. The radiation pressure in massive stellar cores becomes significant, contributing substantially to the support against gravity. In the most massive stars, radiation pressure can exceed gas pressure, creating conditions where the star approaches the Eddington limit, the maximum luminosity a star can sustain, before radiation pressure begins to drive mass loss from the surface. Stars above approximately 100 solar masses flirt with this limit, their outer layers buffeted by the intense radiation streaming outward from the CNO burning core. The interior of a star is not a uniform furnace, but a layered structure where energy moves through distinct mechanisms depending on the local conditions of temperature, density, and opacity. Understanding how energy travels from the nuclear burning core to the stellar surface reveals the intricate physics that governs stellar structure, a physics that varies dramatically between stars of different masses. In the Sun, the core extends outward to approximately 25% of the stellar radius, a region where temperatures exceed 15 million Kelvin and densities reach 150 grams per cubic centimeter, roughly 13 times denser than lead. Here, the proton-proton chain releases energy in the form of gamma-ray photons, each carrying millions of electron volts of energy. These photons cannot simply stream outward unimpeded. The core plasma is so dense and opaque that a photon travels only a fraction of a centimeter before colliding with an electron or ion, being absorbed and re-emitted in a random direction. This process of absorption and re-emission constitutes radiative energy transport, and it dominates the region surrounding the core known as the radiative zone. In the Sun, this zone extends from the outer edge of the core at approximately 0.25 solar radii to about 0.7 solar radii, a shell of plasma where energy creeps outward through countless photon interactions. The journey is extraordinarily slow. A photon generated in the core undergoes so many scatterings, each sending it in a random direction, that the average time for energy to traverse the radiative zone exceeds 100,000 years. Some estimates place this radiative diffusion time closer to 170,000 years, a testament to the opacity of stellar plasma. The opacity of stellar material determines how easily radiation can pass through it. This quantity depends on the chemical composition, temperature, and density of the plasma. At the temperatures found in the radiative zone, between 2 million and 7 million Kelvin, the primary sources of opacity are bound-free absorption, where photons ionize atoms, and free absorption, where photons scatter off electrons in the presence of ions. The opacity increases as temperature decreases, meaning that as energy moves outward into cooler regions, the plasma becomes progressively more resistant to radiative transport. At a critical boundary, approximately 70% of the way from the Sun's center to its surface, the temperature drops to around 2 million Kelvin and the opacity rises sharply. Here, partially ionized hydrogen and helium atoms become efficient absorbers of radiation, creating a bottleneck in the outward flow of energy. The radiative gradient, the rate at which temperature must decrease with radius to transport energy by radiation, becomes steeper than the adiabatic gradient, the rate at which a rising parcel of gas would cool due to expansion. When this condition is met, the plasma becomes convectively unstable. Convection begins when a parcel of gas, slightly hotter than its surroundings, expands and becomes less dense. Buoyancy forces push this parcel upward, carrying its thermal energy with it. As it rises into regions of lower pressure, it expands and cools. but if it remains warmer than the surrounding material, it continues to rise. Eventually, the parcel reaches a level where it matches the temperature of its environment, deposits its excess energy, and sinks back down. This circulation of rising hot gas and sinking cool gas constitutes convective energy transport, and it is far more efficient than radiative diffusion. The outer 30% of the Sun's radius comprises the convective zone, a region of churning plasma where energy moves upward through bulk fluid motions rather than photon diffusion. The convective cells span a range of scales, from granules approximately 1,000 kilometers across that cover the visible solar surface to supergranules 30,000 kilometers in diameter. Beneath the surface, giant convective cells may extend through much of the convective zone, though their structure remains an active area of helioseismological research. The boundary between the radiative and convective zones, called the tachocline, is a region of profound importance for solar physics. Here, the rigid rotation of the radiative zone, which rotates approximately as a solid body with a period of about 27 days, meets the differential rotation of the convective zone, where equatorial regions rotate faster than polar regions. This shear layer is believed to be the site where the solar magnetic field is generated and amplified through dynamo processes, the engine that drives the 11-year solar activity cycle. The structure of stellar interiors changes dramatically with stellar mass. In stars less massive than about 0.35 solar masses, the fully convective red dwarfs, the entire star from center to surface, transports energy through convection. These stars lack a radiative zone entirely because their low core temperatures, around 4 million Kelvin, result in high opacities throughout. The convective mixing extends all the way to the core, continuously replenishing the nuclear-burning region with fresh hydrogen and carrying fusion products outward. This thorough mixing is one reason red dwarfs can sustain hydrogen fusion for trillions of years. Moving up the mass scale, stars between 0.35 and approximately 1.2 solar masses share the Sun's basic structure: a radiative zone surrounding the core and a convective envelope at the surface. The depth of the convective envelope decreases with increasing mass. A star of 0.5 solar masses has a convective zone extending inward to about 40% of its radius, while a star of 1.2 solar masses has a much thinner convective layer, perhaps only the outer 10% of its radius. Above approximately 1.2 solar masses, a fundamental transition occurs. The CNO cycle becomes the dominant energy source, and its extreme temperature sensitivity concentrates energy generation into a small central region. The energy flux emerging from this compact core is so intense that the temperature gradient becomes superadiabatic, triggering convection in the core itself. Simultaneously, the higher surface temperatures of these more massive stars result in lower opacities in the outer layers, allowing radiative transport to dominate there. The structure inverts. Massive stars have convective cores and radiative envelopes, the opposite of the solar configuration. A star of 10 solar masses possesses a convective core extending to approximately 25% of its radius, surrounded by a radiative envelope that reaches to the surface. The convective core continuously mixes fresh hydrogen fuel into the burning region while distributing the helium ash throughout the convective volume. This mixing has profound consequences for stellar evolution, effectively increasing the fuel supply available to the star and altering its evolutionary track. The boundary of a convective core is not perfectly sharp. Convective plumes rising from the core carry momentum that can carry them beyond the formal boundary defined by the Schwarzschild criterion, the condition where radiative and adiabatic gradients are equal. This convective overshooting extends the mixed region by a fraction of a pressure scale height, typically between 0.1 and 0.3 scale heights, depending on the stellar mass and the treatment in stellar models. The extent of overshooting significantly affects predictions of stellar lifetimes and the masses of the helium cores that form after main sequence evolution. The temperature stratification within a star follows from these energy transport mechanisms. In radiative zones, the temperature gradient is determined by the opacity and the energy flux, following the radiative diffusion equation. In convective zones, the temperature gradient is very close to adiabatic, meaning that rising and falling parcels of gas exchange negligible heat with their surroundings. The adiabatic gradient depends on the equation of state of the stellar plasma, particularly the ratio of specific heats, which is influenced by the ionization state of the gas. Near the stellar surface, where convection meets the photosphere, the physics becomes particularly complex. Convective cells overshoot into the stable atmosphere, creating the granulation pattern visible on the solar surface. The tops of granules, where hot plasma rises and spreads horizontally, appear bright, while the intergranular lanes, where cooled plasma descends, appear darker. The temperature contrast between granule centers and lanes is approximately 400 Kelvin, and the typical granule lifetime is about 8 to 10 minutes before it dissipates and is replaced by new convective cells. The sound waves generated by convective motions propagate through the stellar interior, reflecting and refracting according to the local sound speed, which depends on temperature and composition. These oscillations, with periods of approximately 5 minutes in the Sun, provide a window into the stellar interior through the science of asteroseismology. By analyzing the frequencies of thousands of oscillation modes, researchers have mapped the internal rotation profile of the Sun, located the base of the convective zone with precision, and measured the helium abundance in the solar envelope. The smallest stars in the universe burn with a patience that defies human comprehension. While the asteroseismic studies of solar-type stars reveal interiors structured into distinct radiative and convective zones, the red dwarfs occupy a fundamentally different regime of stellar physics, one where convection dominates from the core to the photosphere, and where nuclear fuel is consumed with such extraordinary efficiency that these dim objects will outlive every other star in the cosmos. Red dwarfs, classified as M-type stars on the spectral sequence, span a mass range from approximately 0.08 solar masses at the lower boundary, the minimum mass required to sustain hydrogen fusion, to roughly 0.45 solar masses at the upper limit. Below 0.08 solar masses, objects cannot achieve the core temperatures necessary for sustained nuclear burning and instead become brown dwarfs, failed stars that slowly cool over cosmic time. Above 0.45 solar masses, the internal structure transitions to include a radiative core, and the star begins to resemble the layered architecture of the Sun. The defining characteristic of red dwarfs lies in their fully convective interiors. Unlike the Sun, where energy generated in the core must first diffuse outward through a radiative zone before reaching the convective envelope, a red dwarf circulates material from its very center to its surface and back again. This continuous mixing has profound consequences for stellar evolution. In a solar mass star, only the hydrogen in the core participates in fusion, perhaps 10% of the total hydrogen content. The remaining 90% sits in the envelope, forever separated from the nuclear furnace by the stable radiative zone. When the core hydrogen is exhausted, the star must undergo dramatic structural changes to continue burning. A red dwarf faces no such limitation. The convective currents that churn through its entire volume continuously replenish the core with fresh hydrogen from the outer layers, while carrying processed material outward. This mixing extends the nuclear burning phase to timescales that dwarf the current age of the universe. A red dwarf with 0.1 solar masses will remain on the main sequence for approximately 10 trillion years, nearly 1,000 times longer than the Sun's 10 billion-year lifespan. The universe itself is only 13.8 billion years old, meaning that no red dwarf that has ever formed has yet had time to exhaust its hydrogen supply. Every red dwarf ever born still burns today. The core temperatures of these diminutive stars reflect their modest masses. Where the Sun's center reaches 15 million Kelvin, a typical red dwarf achieves core temperatures between 3 and 5 million Kelvin. This cooler environment dramatically reduces the rate of nuclear fusion. The proton-proton chain, which powers all red dwarfs just as it powers the Sun, proceeds at a pace determined by the probability of quantum tunneling through the Coulomb barrier. This probability depends exponentially on temperature, so even a modest reduction in core temperature translates to an enormous decrease in energy production. A red dwarf with 0.1 solar masses produces energy at a rate of approximately 0.001 solar luminosities, 1,000th the power output of the Sun. This feeble luminosity emerges from a photosphere with an effective temperature between 2,300 and 3,800 Kelvin, compared to the Sun's 5,778 Kelvin. The peak wavelength of emission, governed by Wien's displacement law, falls in the near-infrared rather than the visible spectrum. To human eyes, these stars appear deep red or orange, though much of their radiation remains invisible. Proxima Centauri, the nearest star to the Sun at a distance of 4.24 light-years, exemplifies the red dwarf population. With a mass of 0.12 solar masses and a radius of 0.15 solar radii, Proxima Centauri generates only 0.0017 solar luminosities. Its surface temperature hovers around 3,042 Kelvin, and its fully convective interior ensures that it will continue fusing hydrogen for approximately 4 trillion years. Despite its proximity, Proxima Centauri is invisible to the naked eye, requiring a telescope to observe its dim glow against the background of brighter, more distant stars. The prevalence of red dwarfs in the galaxy is staggering. Approximately 70 to 75% of all stars in the Milky Way belong to the M-dwarf class. Within 10 parsecs of the Sun, roughly 33 light-years, surveys have identified over 350 red dwarfs, compared to fewer than 30 stars of solar type or greater. This numerical dominance arises from the initial mass function, the statistical distribution that describes how many stars of each mass form from a given molecular cloud. Low-mass stars form far more readily than high-mass stars, a consequence of the fragmentation physics in collapsing gas clouds. The magnetic activity of red dwarfs presents a striking contrast to their low luminosities. These small stars generate powerful magnetic fields through dynamo processes driven by their rapid rotation and fully convective interiors. Young red dwarfs can exhibit surface magnetic field strengths exceeding several thousand Gauss compared to the Sun's average field of 1 to 2 Gauss. This intense magnetism produces frequent and violent flares, sudden releases of magnetic energy that can temporarily increase the star's brightness by factors of 10 or more. Proxima Centauri experiences super flares that release energies exceeding 10 to the power of 33 ergs, events that would be catastrophic for any planets in close orbit. In March 2016, observers detected a flare from Proxima Centauri that increased its brightness by a factor of 68 in the far ultraviolet, bathing its planetary system in intense radiation. Such flares occur with frequencies of several per day on active red dwarfs, though their intensity diminishes as the star ages and its rotation slows. The habitable zones around red dwarfs lie extremely close to the star, a consequence of their low luminosities. For Proxima Centauri, the habitable zone extends from approximately 0.04 to 0.08 astronomical units, placing any potentially habitable planet in an orbit with a period of just 11 to 23 Earth days. At such close distances, tidal forces from the star would likely lock the planet into synchronous rotation, presenting one face permanently toward the star, while the other remains in eternal darkness. The evolutionary endpoint of red dwarfs remains theoretical, as none has yet reached it. Models predict that as a red dwarf exhausts its hydrogen over trillions of years, it will gradually contract and heat, briefly becoming a blue dwarf before finally cooling into a helium-white dwarf. Unlike the carbon-oxygen white dwarfs produced by solar mass stars, these helium remnants would form without ever igniting helium fusion, their masses too low to achieve the 100 million Kelvin threshold required for the triple alpha process. The mass of a star at its birth determines nearly everything about its future, from the temperature of its surface to the duration of its existence, from the elements it will forge in its core to the manner of its eventual death. This single property, measured in units of solar masses, acts as a cosmic blueprint that prescribes the entire evolutionary pathway a star will follow across its lifetime. A star of one solar mass, like the Sun, settles onto the main sequence with a surface temperature of approximately 5,800 Kelvin and a luminosity that defines the standard by which all other stellar brightnesses are measured. Its core maintains a temperature of 15 million Kelvin, sufficient to sustain the proton-proton chain, but not hot enough for the CNO cycle to dominate. At this mass, the star will remain on the main sequence for roughly 10 billion years, converting 600 million tons of hydrogen into helium every second while maintaining the delicate balance of hydrostatic equilibrium. Double the mass, and the stellar parameters shift dramatically. A two-solar mass star burns with a surface temperature near 9,000 Kelvin, appearing white to human eyes rather than yellow. Its luminosity increases not by a factor of 2, but by approximately 16, following the mass-luminosity relation that governs main sequence stars. This relationship, expressed mathematically as luminosity proportional to mass raised to the power of 3.5, explains why massive stars exhaust their fuel so rapidly. The two-solar mass star will spend only about 2 billion years on the main sequence, its greater gravitational compression demanding higher core temperatures and faster fusion rates to maintain equilibrium. At 10 solar masses, the star enters a different regime entirely. The core temperature exceeds 25 million Kelvin, and the CNO cycle becomes the dominant energy source, its temperature sensitivity causing the core to become convective while the outer layers transport energy through radiation. The surface blazes at 25,000 Kelvin, emitting most of its light in the ultraviolet spectrum invisible to human eyes. Such a star shines with a luminosity 10,000 times that of the Sun, yet this prodigious output comes at a cost. The main sequence lifetime shrinks to roughly 20 million years, a mere heartbeat in cosmic terms. The most massive stars known push these relationships to their extremes. A star of 60 solar masses, near the upper limit of stellar formation, achieves core temperatures exceeding 40 million Kelvin. Its luminosity approaches 1 million times solar, and radiation pressure within its interior becomes comparable to gas pressure, fundamentally altering the physics of its structure. The Eddington limit, the theoretical maximum luminosity at which radiation pressure would overcome gravitational binding, constrains how bright such stars can become. These stellar giants will exhaust their core hydrogen in as little as 3 million years, their brief lives ending in spectacular supernovae that seed the interstellar medium with heavy elements. At the opposite extreme, stars of 0.5 solar masses demonstrate the consequences of low mass. With core temperatures barely exceeding 8 million Kelvin, these orange dwarfs rely entirely on the proton-proton chain, their fusion rates so modest that main sequence lifetimes extend to 50 billion years or more. Their fully convective interiors ensure complete mixing of hydrogen fuel, allowing them to burn a larger fraction of their total mass than more massive stars whose radiative cores trap helium ash in the center. The position of a star on the Hertzsprung-Russell diagram, the fundamental tool astronomers use to classify stellar populations, reflects these mass-dependent properties. This diagram plots luminosity against surface temperature, and main sequence stars form a diagonal band running from hot, luminous blue giants in the upper left to cool, dim red dwarfs in the lower right. A star's location along this band is determined almost entirely by its mass, with higher mass stars occupying the upper regions and lower mass stars the lower regions. The main sequence is not a static location, but a slow evolutionary track. As a star converts hydrogen to helium in its core, the mean molecular weight of the core material increases. Helium nuclei contain 4 nucleons, but carry only 2 units of positive charge, meaning fewer particles exist per unit mass compared to hydrogen. This reduction in particle number decreases the gas pressure at a given temperature and density, requiring the core to contract slightly and heat up to maintain hydrostatic equilibrium. This gradual core contraction causes the star to brighten over its main sequence lifetime. The Sun today is approximately 30% more luminous than it was 4.6 billion years ago when it first reached the main sequence. In another 5 billion years, it will be nearly twice as bright as it is now, its increased luminosity eventually rendering Earth's surface too hot for liquid water. This slow brightening occurs for all main sequence stars, causing them to drift slightly upward and to the right on the Hertzsprung-Russell diagram as they age. The internal structure of a main sequence star varies systematically with mass. Stars below approximately 0.35 solar masses are fully convective, their interiors churning like boiling water from core to surface. Between 0.35 and 1.2 solar masses, stars develop a radiative core surrounded by a convective envelope, with the boundary between these zones depending on the local temperature gradient. Above 1.2 solar masses, the pattern reverses, with convective cores driven by the temperature-sensitive CNO cycle, surrounded by radiative envelopes where the temperature gradient is too shallow to drive convection. These structural differences have profound consequences for stellar evolution. In stars with radiative cores, the helium produced by fusion remains trapped in the center, building up an inert helium core that grows denser over time. The hydrogen-burning shell that will eventually form at the edge of this core drives the post-main sequence evolution of such stars. In fully convective stars, by contrast, fresh hydrogen continuously mixes into the core, extending the main sequence lifetime and preventing the formation of a distinct helium core until much later in the star's life. The chemical composition of a star also influences its main sequence properties, though less dramatically than mass. Stars with higher metallicity, the astronomical term for elements heavier than helium, have slightly higher opacities in their outer layers, trapping radiation more effectively and causing the star to expand slightly at a given mass. This effect shifts metal-rich stars to cooler temperatures and higher luminosities compared to their metal-poor counterparts, a difference visible in the color magnitude diagrams of stellar populations with different chemical histories. The rotation rate of a star affects its main sequence evolution through several mechanisms. Rapid rotation induces mixing currents that can transport fresh hydrogen into the core, extending the main sequence lifetime. It also causes the star to become oblate, with the equatorial regions bulging outward and cooling relative to the poles. In extreme cases, rotation can approach the critical velocity at which centrifugal force at the equator equals gravitational attraction, causing the star to shed mass from its equatorial regions. Binary star systems, which comprise roughly half of all stellar systems, introduce additional complications to main sequence evolution. Close binaries can exchange mass through Roche lobe overflow, fundamentally altering the evolutionary paths of both components. A star that accretes mass from its companion may rejuvenate, gaining fresh hydrogen fuel and appearing younger than its true age. The donor star, stripped of its outer layers, may evolve into configurations impossible for single stars to achieve. The end of the main sequence phase arrives when the core hydrogen is exhausted, leaving behind a helium core surrounded by a hydrogen-burning shell. The timing of this transition depends critically on mass. For the Sun, this moment lies approximately 5 billion years in the future. For a star of 15 solar masses, it occurred within the first 10 million years of the star's existence. For a red dwarf of 0.1 solar masses, it will not arrive for another 10 trillion years, long after the last galaxies have faded and the universe has grown cold and dark. The exhaustion of hydrogen in a stellar core marks not a sudden death, but the beginning of a profound restructuring, a transition that unfolds over timescales measured in hundreds of millions of years for a star like the Sun. The core, once a site of furious nuclear activity where 600 million tons of hydrogen transformed into helium every second, grows quiet. The temperature remains extreme, hovering near 15 million Kelvin, but without fresh hydrogen nuclei to fuse, the proton-proton chain sputters and fails. The helium ash that accumulated over billions of years now dominates the core, inert and compressed, unable to ignite, because helium fusion requires temperatures nearly 10 times higher than hydrogen burning. The immediate consequence of this nuclear silence is a loss of radiation pressure from the core. For billions of years, the outward push of photons generated by fusion balanced the inward crush of gravity, maintaining the delicate equilibrium called hydrostatic balance. When fusion ceases, gravity gains the upper hand. The helium core begins to contract, slowly at first, then with increasing determination. This contraction is not a collapse in the catastrophic sense, but a gradual compression that releases gravitational potential energy, converting the inward motion of matter into heat. The physics of this contraction follows the virial theorem, one of the most elegant relationships in stellar astrophysics. As the core shrinks, half of the gravitational energy released heats the core itself, while the other half radiates away into the surrounding stellar material. The core temperature rises even as fusion has stopped, climbing from 15 million Kelvin toward 20 million, then 30 million. The density increases in parallel, the helium nuclei packing ever more tightly together. In the Sun's future helium core, the density will eventually reach approximately 100,000 grams per cubic centimeter, 100 times denser than the core during the main sequence phase. Surrounding this contracting helium core lies a shell of hydrogen-rich material that has never experienced the temperatures necessary for fusion. As the core contracts and heats, this shell finds itself in an environment increasingly favorable for nuclear reactions. The temperature at the base of the hydrogen shell rises past the 10 million Kelvin threshold, and fusion ignites in a thin layer wrapped around the helium core like the skin of an onion. This hydrogen shell burning marks the birth of the subgiant phase, a transitional state between the main sequence and the red giant branch. Shell burning operates under different physics than core burning. In the core, fusion occurred throughout a large volume, the reactions distributed across a sphere, perhaps 200,000 kilometers in diameter. In the shell, fusion concentrates in a thin layer only a few thousand kilometers thick, wrapped around a core that may be only Earth-sized, despite containing a substantial fraction of the star's mass. The energy generation rate in this shell can exceed the main sequence luminosity because the shell temperature often surpasses the original core temperature, and the density of fuel remains high. The energy produced by hydrogen shell burning must escape through the overlying stellar envelope, and this energy flux has dramatic consequences for the star's structure. The envelope, receiving more energy from below than it can efficiently transport, begins to expand. The surface of the star swells outward, its radius increasing from the solar value of approximately 700,000 kilometers toward dimensions that will eventually encompass the orbit of Mercury. As the surface area grows, the same luminosity spreads across a larger sphere, and the effective temperature drops. The star reddens, its peak emission shifting from yellow-white toward orange. This expansion proceeds gradually during the subgiant phase. A star of one solar mass spends roughly 2 billion years as a subgiant, its radius growing from 1 solar radius to perhaps 2 or 3 solar radii, its surface temperature declining from 5,800 Kelvin toward 5,000 Kelvin. The luminosity increases modestly during this phase, perhaps doubling or tripling as the shell burning intensifies and the contracting core releases gravitational energy. On the Hertzsprung-Russell diagram, the star traces a path rightward and slightly upward, departing from the main sequence toward the red giant branch. The internal structure of a subgiant reveals the complexity of stellar evolution. The helium core, now isothermal because electron conduction efficiently distributes heat, sits at the center like a dense, hot seed. Surrounding it, the hydrogen-burning shell generates energy at a prodigious rate, the proton-proton chain, or CNO cycle, operating in a narrow zone where conditions permit fusion. Above the shell lies a radiative zone where photons carry energy outward, their journey taking thousands of years as they scatter from atom to atom. Near the surface, convection takes over, giant cells of plasma rising and falling as heat drives circulation patterns that span hundreds of thousands of kilometers. The mass of the star profoundly influences the subgiant transition. Stars below approximately 0.4 solar masses never develop the distinct core shell structure because convection mixes their entire interiors, preventing the accumulation of a helium core. These fully convective red dwarfs simply fade when their hydrogen is exhausted, never experiencing the subgiant or red giant phases. Stars between 0.4 and approximately 2.3 solar masses develop degenerate helium cores during the subgiant phase, the electrons in the core becoming quantum, mechanically constrained in ways that dramatically affect later evolution. Stars above 2.3 solar masses maintain non-degenerate cores, their higher temperatures preventing the onset of electron degeneracy. Electron degeneracy in the helium core represents a quantum mechanical phenomenon with profound consequences. As the core contracts and density increases, the electrons are squeezed into ever smaller volumes. The Pauli exclusion principle forbids two electrons from occupying the same quantum state, and as the available states fill, the electrons exert a pressure that resists further compression regardless of temperature. This degeneracy pressure depends only on density, not temperature, which means the core can heat without expanding. The decoupling of temperature and pressure sets the stage for the helium flash that will eventually occur in lower mass stars. The hydrogen-burning shell advances outward through the star as it consumes fuel, leaving behind additional helium ash that settles onto the growing core. The core mass increases steadily, from perhaps 0.1 solar masses at the end of the main sequence toward the 0.45 to 0.5 solar masses required to ignite helium fusion. This growth takes hundreds of millions of years, the shell burning through the hydrogen reservoir at a rate determined by the luminosity demands of the expanding envelope. Surface abundances begin to change during the subgiant phase as convection dredges material from deeper layers. The first dredge up, as astronomers call this mixing event, brings helium and nitrogen-enriched material to the surface while diluting the original carbon and oxygen abundances. Spectroscopic observations of subgiant stars reveal these altered compositions, the carbon-to-nitrogen ratio declining as CNO processed material mixes into the photosphere. Lithium, fragile and easily destroyed at temperatures above 2.5 million Kelvin, disappears almost entirely from the surface as convection carries it into hotter regions. The subgiant branch represents a relatively brief phase in stellar evolution, a transition zone between the long stability of the main sequence and the dramatic expansion of the red giant phase. For the Sun, this transition will occupy roughly 1 billion years, a mere fraction of its 10 billion-year main sequence lifetime. During this period, the Sun's luminosity will increase by approximately a factor of 2, and its radius will grow to perhaps twice its current value. Earth's oceans will evaporate, its atmosphere will be stripped away, and the planet will become a scorched, lifeless world long before the Sun reaches the tip of the red giant branch. The physics driving this transition operates with mechanical precision, each stage following inevitably from the laws of gravity, thermodynamics, and nuclear physics. The star has no choice in its evolution, no capacity to resist the changes imposed by the exhaustion of its fuel. The same processes that created the conditions for life during the main sequence now drive the star toward configurations that will sterilize any worlds orbiting within the expanding photosphere. The subgiant phase is neither beginning nor end, but a passage, a transformation from one state of equilibrium to another, governed by the same physical principles that have shaped every star since the first generation ignited in the young universe. The transformation accelerates as the hydrogen-burning shell continues its relentless march outward through the star's envelope. What began as a gradual swelling during the subgiant phase now enters a dramatic expansion that will increase the star's radius by a factor of 100 or more. A solar mass star that once measured 1.4 million kilometers across will grow to encompass a volume that could swallow the orbit of Mercury, then Venus, and eventually approach the current position of Earth itself. This expansion is not a gentle inflation, but the consequence of a fierce battle between the contracting core and the energy pouring outward from the shell source that surrounds it. The core itself continues to compress under its own gravity, no longer supported by the energy generation that once maintained its equilibrium. Helium nuclei, the ash of 4 billion years of hydrogen fusion, pack ever more tightly together as the core shrinks. The density climbs toward extraordinary values, reaching 100,000 grams per cubic centimeter in a solar mass star, roughly 100 times denser than the core during the main sequence. At these densities, a teaspoon of core material would weigh as much as a small automobile. The temperature rises in response to this compression, climbing from the 15 million Kelvin of the main sequence toward the 100 million Kelvin threshold required to ignite helium fusion, though this ignition remains millions of years away for a star of solar mass. The hydrogen-burning shell operates with an efficiency that seems almost paradoxical. As the core contracts and heats, the shell grows hotter as well, and the rate of nuclear reactions increases dramatically. The luminosity of a red giant can exceed that of the main sequence star by factors of 1,000 or more. Yet this enormous energy output emerges from a shell only a few thousand kilometers thick. The shell burns through its fuel rapidly, converting hydrogen to helium at rates that would have exhausted the entire core supply in a fraction of the main sequence lifetime. But the shell is not consuming a fixed reservoir. As it burns, it moves outward into fresh hydrogen, leaving behind more helium ash that settles onto the growing core. The envelope responds to this increased energy input by expanding, and the physics of this expansion reveals the intimate connection between stellar interiors and surfaces. The energy generated in the shell must traverse the entire envelope before escaping into space, and the opacity of stellar material determines how this energy flows. In the deep interior, where temperatures exceed several million Kelvin, energy moves primarily through radiation, photons scattering from electron to electron in a random walk that can take thousands of years to traverse the stellar radius. But as the envelope expands and cools, the opacity increases dramatically. Partially ionized hydrogen and helium atoms absorb photons far more efficiently than fully ionized plasma, creating a bottleneck that traps energy in the outer layers. This trapped energy drives convection, the physical transport of hot material upward and cool material downward. In a red giant, convection dominates the envelope structure, with enormous cells of rising and falling gas that can span significant fractions of the stellar radius. The convective envelope of a red giant extends from just above the hydrogen-burning shell all the way to the photosphere, a continuous churning that mixes material from deep within the star to its visible surface. This mixing has observable consequences. Elements produced by nuclear reactions in the interior, or modified by partial processing in the shell, can be dredged up to the surface where spectroscopy reveals their presence. The carbon-to-nitrogen ratio changes as material processed by the CNO cycle reaches the photosphere, providing direct evidence of the nuclear burning occurring far below. The surface temperature drops as the star expands, falling from the 5,800 Kelvin of a solar-type main sequence star to approximately 3,500 Kelvin in the red giant phase. This cooling shifts the peak of the star's radiation from yellow-white light toward the red end of the spectrum, giving red giants their characteristic color. The lower temperature also allows molecules to form in the stellar atmosphere, compounds like titanium oxide and water vapor that cannot exist in the hotter photospheres of main sequence stars. These molecules create distinctive absorption bands in the stellar spectrum, dark regions where specific wavelengths of light are absorbed by molecular transitions. The mass loss that began tentatively during the subgiant phase intensifies as the red giant expands. The surface gravity decreases as the radius grows, falling to values 100 times lower than the main sequence surface gravity. At these low gravities, the outer atmosphere is barely bound to the star, and radiation pressure combined with convective motions can drive material outward into space. A red giant loses mass at rates of approximately 100 millionth of a solar mass per year, a gentle breeze compared to the violent winds of more evolved phases, but significant over the millions of years the star spends as a red giant. This lost material forms a tenuous circumstellar envelope, a shell of gas and dust that surrounds the star and gradually disperses into the interstellar medium. The timescale of red giant evolution depends critically on stellar mass. A solar mass star spends approximately 1 billion years ascending the red giant branch, a duration set by the rate at which the hydrogen shell burns through the envelope and the core contracts toward helium ignition. More massive stars evolve more rapidly, their higher luminosities consuming fuel at accelerated rates. A 5 solar mass star completes its red giant evolution in roughly 100 million years, while a star of 8 solar masses races through this phase in only 20 million years. The most massive stars, those exceeding about 10 solar masses, evolve so rapidly that they barely pause in the red giant region of the Hertzsprung-Russell diagram, their cores heating to helium ignition temperatures almost immediately after hydrogen exhaustion. The structure of a red giant presents a study in contrasts. The core, though containing only a small fraction of the total mass, occupies a volume smaller than the Earth, a sphere perhaps 20,000 kilometers in diameter, compressed to densities that approach those of atomic nuclei. Surrounding this dense core, the hydrogen-burning shell generates energy at prodigious rates, its thin geometry concentrating nuclear reactions into a region that would fit comfortably within the volume of a terrestrial planet. Beyond the shell, the envelope extends outward for tens of millions of kilometers, a vast atmosphere of tenuous gas with densities that decrease exponentially with radius until they merge imperceptibly with the vacuum of interstellar space. The gravitational binding of this extended envelope becomes increasingly precarious as evolution proceeds. The escape velocity at the surface of a red giant can fall below 20 kilometers per second, compared to over 600 kilometers per second at the surface of the Sun. Thermal motions in the photosphere, combined with the momentum imparted by radiation pressure, can accelerate atoms to velocities approaching this escape threshold. The outer layers of a red giant exist in a state of marginal stability, bound to the star, but susceptible to any perturbation that might provide the additional energy needed for escape. The core continues its inexorable contraction throughout the red giant phase, and as it shrinks, a new physical phenomenon begins to assert itself. At the densities achieved in the cores of red giants, electrons are forced so close together that quantum mechanical effects become important. The Pauli exclusion principle forbids electrons from occupying identical quantum states, and as the density increases, electrons are forced into higher and higher energy states simply because all lower states are already occupied. This creates a pressure that resists further compression, a quantum mechanical effect known as electron degeneracy pressure that operates independently of temperature. The onset of degeneracy changes the physics of the core in fundamental ways. In a normal gas, pressure depends on both density and temperature, and heating a gas increases its pressure. But in a degenerate gas, pressure depends primarily on density alone. Heating a degenerate core does not significantly increase its pressure, which means the core cannot expand to cool itself when nuclear reactions begin. This peculiarity will have dramatic consequences when the core eventually reaches helium ignition temperatures, consequences that will manifest in one of the most violent events in stellar evolution. The degenerate core continues its slow contraction, growing ever denser and hotter over millions of years as the hydrogen-burning shell deposits fresh helium ash onto its surface. The core's temperature climbs steadily, passing 50 million Kelvin, then 60, then 70. Throughout this gradual heating, the electron degeneracy pressure holds firm, preventing the core from expanding even as thermal energy accumulates within it. The core becomes a pressure cooker with no relief valve, storing energy that cannot escape through the normal mechanism of expansion and cooling. At approximately 100 million Kelvin, the helium nuclei finally possess enough kinetic energy to overcome their mutual electromagnetic repulsion. Two helium-4 nuclei, each carrying 2 protons and 2 neutrons, collide with sufficient violence to briefly fuse into beryllium-8. This isotope is extraordinarily unstable, with a half-life of merely 8.19 times 10 to the negative 17th seconds, a duration so brief that it seems impossible for any further reaction to occur. Yet at the extreme densities of the degenerate core, where matter is packed to approximately 1 million grams per cubic centimeter, the probability of a third helium nucleus striking the beryllium-8 before it decays becomes significant. When this collision occurs, carbon-12 forms through what physicists call the triple alpha process, named for the 3 alpha particles, which is simply another name for helium-4 nuclei that combine to create it. The first fusion reactions release energy, but unlike in a normal gas, this energy does not cause the core to expand. The degenerate electrons, locked into their quantum states by the Pauli exclusion principle, maintain their pressure regardless of temperature. The core cannot cool itself through expansion, so the temperature rises further. Higher temperatures accelerate the fusion rate, which releases more energy, which raises the temperature even more. This positive feedback loop, called a thermonuclear runaway, causes the core's energy output to increase exponentially over a timescale of mere seconds. Within those few seconds, the core of a red giant releases energy at a rate comparable to the entire luminosity of the Milky Way galaxy. The power output reaches approximately 10 to the 11th solar luminosities, 100 billion times the energy our Sun produces in the same interval. This is the helium flash, one of the most violent events in stellar evolution, yet paradoxically one that remains entirely invisible from the outside of the star. The violence of the helium flash is contained entirely within the degenerate core, buried beneath hundreds of thousands of kilometers of stellar envelope. The energy released cannot escape directly because the overlying layers are opaque to radiation, and the timescale of the flash is far too brief for the energy to diffuse outward through the star's bulk. Instead, the energy goes into heating the core itself, finally raising its temperature high enough that the electrons cease to be degenerate. At approximately 350 million Kelvin, the thermal energy of the particles becomes comparable to the Fermi energy of the degenerate electrons, and normal gas behavior resumes. Once degeneracy lifts, the core can finally respond to its extreme temperature in the expected way. It expands rapidly, and this expansion cools the helium-burning region, reducing the fusion rate and ending the runaway. The entire process, from the first helium fusion reactions to the lifting of degeneracy, occurs in a matter of minutes to hours, though the exact duration depends on the mass and composition of the star. The core settles into a new equilibrium, now burning helium steadily in its center, while hydrogen continues to fuse in a shell surrounding it. The aftermath of the helium flash leaves the star fundamentally restructured. The core, no longer degenerate, has expanded to roughly 10 times its pre-flash radius, though it remains tiny compared to the bloated envelope. The core temperature stabilizes at approximately 100 to 200 million Kelvin, hot enough to sustain steady helium fusion through the triple alpha process. Each fusion reaction converts 3 helium-4 nuclei with a combined mass of 12.09 atomic mass units into 1 carbon-12 nucleus with a mass of exactly 12 atomic mass units. The missing 0.09 atomic mass units, representing about 0.07% of the original mass, transforms into energy according to Einstein's equation, providing 7.275 million electron volts per reaction. The star's position on the Hertzsprung-Russell diagram shifts dramatically following the helium flash. It moves from the red giant branch to a region called the horizontal branch, named for the roughly horizontal distribution of stars at this evolutionary stage when plotted by luminosity and temperature. The surface temperature increases as the envelope contracts somewhat, while the luminosity decreases from its red giant peak. A star like the Sun will settle at approximately 50 solar luminosities during this phase, compared to the 2,000 solar luminosities it reached at the tip of the red giant branch. The horizontal branch phase represents a period of relative stability, a second main sequence of sorts where helium fusion in the core balances gravitational contraction. However, this stability is far more fleeting than the hydrogen-burning main sequence. The helium fuel supply is smaller than the original hydrogen reservoir, and the triple alpha process is less efficient at converting mass to energy. A solar mass star will exhaust its core helium in approximately 100 million years, roughly 1% of the time it spent burning hydrogen on the main sequence. As helium fusion proceeds, the core gradually transforms from helium to carbon and oxygen. Some of the carbon-12 produced by the triple alpha process captures an additional helium-4 nucleus to form oxygen-16, releasing 7.162 million electron volts in the process. The relative proportions of carbon and oxygen in the final core depend on the temperature and density conditions. but typically the core ends up with roughly equal parts of each element by mass. This carbon-oxygen mixture will eventually form the composition of the white dwarf that remains after the star sheds its outer layers. The horizontal branch is not entirely peaceful. The star continues to lose mass through stellar winds, though at a reduced rate compared to the red giant phase. The hydrogen-burning shell remains active, adding processed material to the helium layer surrounding the core. Meanwhile, convection in the outer envelope occasionally dredges up material from deeper layers, mixing the products of nuclear fusion into the observable surface. Spectroscopic observations of horizontal branch stars reveal enhanced abundances of carbon and nitrogen compared to their main sequence progenitors, evidence of this internal mixing. The structure of a horizontal branch star resembles a nested series of shells, each with distinct physical conditions and energy generation mechanisms. At the very center lies the helium-burning core, approximately 1/10 of a solar mass, with temperatures exceeding 100 million Kelvin and densities of several thousand grams per cubic centimeter. Surrounding this is a thin helium layer, the ash from previous hydrogen burning that has not yet reached ignition temperature. Above that burns the hydrogen shell, still converting hydrogen to helium at temperatures of approximately 20 million Kelvin. Finally, the vast convective envelope extends outward, carrying energy to the surface through the churning motion of hot gas rising and cool gas sinking. The helium-burning core at the heart of a horizontal branch star hosts one of the most remarkable nuclear reactions in the universe, a process so improbable that its very existence puzzled physicists for decades. The triple alpha process, named for the 3 helium nuclei it consumes, transforms the simplest fusion product into the element that forms the backbone of all organic chemistry. Without this reaction, carbon would not exist in the quantities we observe, and the universe would be a fundamentally different place. The challenge begins with the structure of helium itself. A helium-4 nucleus, also called an alpha particle, contains 2 protons and 2 neutrons bound together with extraordinary stability. When 2 helium nuclei collide and fuse, they create beryllium-8, an isotope with 4 protons and 4 neutrons. But beryllium-8 is spectacularly unstable, existing for only about 10 to the negative 16 seconds before splitting back into 2 helium nuclei. This fleeting existence, roughly 1/10 quadrillionth of a second, would seem to make further fusion impossible. The beryllium simply does not survive long enough for a 3rd helium nucleus to find it and complete the reaction. Yet the reaction does proceed, and understanding why requires examining the extreme conditions within the stellar core. At temperatures exceeding 100 million Kelvin, helium nuclei move at average speeds of approximately 1,000 kilometers per second. The core density of several thousand grams per cubic centimeter means that these particles are packed extraordinarily close together, with typical separations of only a few femtometers. Under these conditions, collisions occur with staggering frequency, roughly 10 to the 34th times per cubic centimeter per second. Even with beryllium-8's vanishingly brief lifetime, the sheer number of collisions ensures that at any given moment, a small but significant population of beryllium-8 nuclei exists within the core. The equilibrium concentration of beryllium-8 depends sensitively on temperature. At 100 million Kelvin, approximately 1 beryllium-8 nucleus exists for every billion helium nuclei. This seems negligible, but in a core containing roughly 10 to the 56 helium nuclei, it translates to approximately 10 to the 47 beryllium-8 nuclei present at any instant. Each of these unstable nuclei represents a fleeting opportunity for the reaction to proceed to the next step. The second stage of the triple alpha process requires a beryllium-8 nucleus to capture a third helium nucleus before it decays. The probability of this occurring would be vanishingly small were it not for a remarkable coincidence discovered by the physicist Fred Hoyle in 1954. Hoyle reasoned that since carbon clearly exists in abundance throughout the universe, there must be some mechanism that enhances the reaction rate. He predicted the existence of an excited state of carbon-12, with an energy level almost exactly matching the combined energy of beryllium-8 and helium-4 at stellar core temperatures. This prediction proved correct. Carbon-12 possesses an excited state at 7.65 million electron volts above its ground state, a value that corresponds almost precisely to the thermal energy available in a helium-burning core. This resonance, now called the Hoyle state, increases the probability of carbon formation by a factor of approximately 10 million compared to what would occur without it. The match is so precise that a difference of just 4% in either direction would render the reaction too slow to produce significant carbon during a star's lifetime. When beryllium-8 captures a helium nucleus, the resulting carbon-12 forms in this excited Hoyle state. The nucleus vibrates with excess energy, and it must shed this energy quickly, or it will simply break apart again into 3 helium nuclei. Approximately 99.6% of the time, this is exactly what happens. The excited carbon nucleus survives for only about 10 to the negative 17 seconds before disintegrating. But in the remaining fraction of a percent of cases, the nucleus releases its excess energy by emitting a gamma-ray photon, dropping to a lower energy state from which it cannot easily break apart. The gamma ray carries away 7.65 million electron volts of energy, leaving behind a stable carbon-12 nucleus in its ground state. This photon streams outward through the stellar material, contributing to the energy that will eventually reach the surface and radiate into space. The newly formed carbon nucleus settles into the growing population of fusion products accumulating in the core. The net energy release from the complete triple alpha process amounts to 7.275 million electron volts per carbon nucleus formed. This is considerably less than the 26.7 million electron volts released when 4 hydrogen nuclei fuse into helium, which explains why helium burning must occur at much higher temperatures to generate comparable luminosity. The reaction rate depends on temperature raised to approximately the 40th power, an extraordinarily steep relationship that makes helium burning exquisitely sensitive to core conditions. A temperature increase of just 10% more than doubles the energy generation rate. The carbon produced by the triple alpha process does not simply accumulate indefinitely. At the temperatures present in helium-burning cores, carbon nuclei can capture additional helium nuclei to form oxygen-16. This reaction proceeds through a resonance as well, though one that is less favorable than the Hoyle state. The result is that helium-burning cores produce a mixture of carbon and oxygen, with the exact ratio depending on the core temperature and density. In typical horizontal branch stars, the final composition settles at approximately equal parts carbon and oxygen by mass. The oxygen-forming reaction releases an additional 7.162 million electron volts per nucleus, adding to the total energy output of the helium-burning core. Further captures of helium nuclei could in principle produce neon-20 and heavier elements, but the temperatures in low-mass stars never reach the threshold required for these reactions to proceed efficiently. The core composition stabilizes as a carbon-oxygen mixture, the ultimate fate of the nuclear fuel in stars below, approximately 8 solar masses. The spatial distribution of these reactions within the core follows the temperature profile precisely. The highest temperatures occur at the very center, where the triple alpha process runs most vigorously. Moving outward, the temperature drops and the reaction rate plummets. The energy generation is concentrated in the innermost regions, creating a steep luminosity gradient that drives convective mixing throughout much of the core. This convection homogenizes the composition, ensuring that fresh helium is continuously supplied to the hottest central regions, while newly synthesized carbon and oxygen are distributed throughout the convective zone. The convective core eventually exhausts its helium fuel, and the star enters yet another phase of profound transformation. The central regions, now composed primarily of carbon and oxygen, begin to contract once more under their own gravity. But for stars below approximately 8 solar masses, the temperatures required to ignite carbon fusion, somewhere around 600 million Kelvin, will never be reached. The core is destined to become inert, a dense sphere of carbon and oxygen that will slowly cool over cosmic time scales. Yet the star's journey is far from over. It now enters the asymptotic giant branch, a phase of stellar evolution marked by extraordinary instability and dramatic mass loss. The structure that emerges during this phase is remarkably complex. At the center lies the dormant carbon-oxygen core, compressed to densities exceeding 1 million grams per cubic centimeter. Surrounding this inert core is a thin shell, where helium continues to fuse into carbon through the triple alpha process. Above this helium-burning shell lies another shell where hydrogen fuses into helium. And enveloping everything is a vast, tenuous envelope that extends outward to distances comparable to the orbit of Mars or even Jupiter in our own solar system. The star has become a nested structure of burning shells, each contributing to the total luminosity in ways that create profound instabilities. The luminosity during the asymptotic giant branch phase increases dramatically compared to the earlier red giant phase. A star that began its life with 1 solar mass might now radiate with a luminosity exceeding 10,000 times that of the present-day Sun. This enormous energy output drives the outer envelope to expand to truly immense proportions, with radii reaching 200 to 300 times the solar radius. The surface temperature drops to around 2,500 to 3,000 Kelvin, giving the star a deep red color that would dominate the night sky of any nearby planet. The dual-shell burning structure creates a peculiar instability known as thermal pulses. The helium-burning shell operates in a fundamentally different manner than the hydrogen-burning shell above it. While hydrogen fusion proceeds steadily, the helium shell tends to burn in episodic bursts, separated by periods of relative quiescence. The physics behind this behavior involves the extreme temperature sensitivity of the triple alpha process. When the helium shell ignites, it releases energy so rapidly that the shell expands and cools, temporarily quenching the nuclear reactions. The shell then contracts, heats up, and eventually reignites in another burst of fusion. These thermal pulses occur with a characteristic period that depends on the stellar mass. For a star of 1 solar mass, the interval between pulses is typically around 100,000 years. More massive asymptotic giant branch stars experience pulses more frequently, with intervals as short as 10,000 to 20,000 years. Each pulse releases an enormous amount of energy in a relatively brief time, perhaps 100 million years worth of steady luminosity compressed into just a few hundred years of intense burning. The consequences of these thermal pulses ripple throughout the entire stellar structure. When the helium shell ignites in a pulse, it generates a convective zone that can extend upward through the intershell region, the layer between the helium and hydrogen burning shells. This convection dredges up material from the deeper layers and mixes it with the outer envelope in a process known as third dredge-up. The material brought to the surface includes freshly synthesized carbon from the helium-burning shell, along with heavy elements produced through a remarkable process called slow neutron capture, or the S process. The S process operates in the intershell region during and between thermal pulses. Free neutrons, released by reactions such as carbon-13 capturing alpha particles, are absorbed by ion group nuclei at a leisurely pace. The neutron flux is low enough that unstable isotopes have time to undergo beta decay before capturing additional neutrons. This slow, stepwise construction of heavier elements produces roughly half of all nuclei heavier than iron, including elements like strontium, barium, and lead. The third dredge-up brings these newly forged heavy elements to the stellar surface, where they can be detected spectroscopically and eventually dispersed into the interstellar medium. The repeated dredge-up episodes gradually transform the surface composition of the star. Initially, the envelope contains more oxygen than carbon, reflecting the cosmic abundance pattern inherited from the interstellar cloud that formed the star. But each thermal pulse brings more carbon to the surface, and eventually the carbon abundance can exceed that of oxygen. When this transition occurs, the star becomes a carbon star, displaying distinctive spectral features from molecules like C2, cene, and silicon carbide. These carbon stars are among the most efficient producers of cosmic dust, forming tiny grains of silicon carbide and graphite in their cool outer atmospheres. The mass loss rate during the asymptotic giant branch phase accelerates dramatically compared to earlier evolutionary stages, while a main sequence star like the Sun loses mass at a rate of roughly 10 to the negative 14 solar masses per year through its solar wind. An asymptotic giant branch star can shed material at rates of 10 to the negative 7 to 10 to the negative 4 solar masses per year. At the highest rates, the star loses an Earth mass of material every few days. This prodigious mass loss is driven by a combination of radiation pressure on dust grains and pulsations that levitate material into regions cool enough for dust to condense. Many asymptotic giant branch stars pulsate with periods ranging from 100 to 1,000 days. These long-period variables, including the famous Mira variables, expand and contract rhythmically as pressure waves propagate through their extended envelopes. The pulsations lift material to greater heights, where temperatures drop below 1,500 Kelvin and allow refractory compounds to condense into solid grains. These dust grains absorb stellar radiation efficiently and are accelerated outward by radiation pressure, dragging gas along with them and creating a dense stellar wind. The circumstellar envelope that accumulates around an asymptotic giant branch star can contain substantial mass, sometimes exceeding a solar mass of material distributed in a shell extending outward for thousands of astronomical units. This material is rich in molecules and dust, creating a complex chemistry that includes water, carbon monoxide, silicon monoxide, and hundreds of other molecular species. Radio telescopes detect these molecules through their rotational transitions, revealing the composition and dynamics of the outflowing material. The thermal pulses grow stronger as the star evolves along the asymptotic giant branch. Each successive pulse releases more energy and drives more vigorous convection. The interpulse period shortens as the core mass grows through the accumulation of helium ash from the hydrogen-burning shell. The core mass increases at a rate of roughly 10 to the -7 solar masses per year, slowly approaching the Chandrasekhar limit of approximately 1.4 solar masses. However, the intense mass loss ensures that most asymptotic giant branch stars will never reach this limit. They will shed their envelopes entirely before the core can grow massive enough to collapse. The final thermal pulses can be particularly violent, sometimes occurring after the star has already begun to shed its envelope and transition toward the planetary nebula phase. These late thermal pulses can temporarily reignite hydrogen burning in dramatic fashion, causing the star to expand and brighten before resuming its contraction. Observations of objects like Sakurai's object and FG Sagittae have captured stars in the midst of such late thermal pulse events, providing direct evidence for the theoretical predictions of stellar evolution models. As the asymptotic giant branch phase progresses, the mass loss eventually strips away nearly the entire hydrogen envelope, exposing the hot interior of the star. The transition occurs when the envelope mass drops below approximately 0.01 solar masses, at which point the star can no longer maintain its extended red giant configuration. The remnant begins to contract and heat up, its surface temperature rising from 3,000 Kelvin toward 30,000 Kelvin and beyond over a timescale of thousands to tens of thousands of years. The intense ultraviolet radiation from this increasingly hot central star begins to ionize the previously ejected envelope, causing it to glow as a planetary nebula. The planetary nebula phase represents one of the most visually spectacular and physically complex stages in the evolution of low to intermediate mass stars. a brief but brilliant display that lasts only 20,000 to 50,000 years before fading into the darkness of interstellar space. The glowing shells of gas that characterize these objects are not static structures, but dynamic, expanding envelopes driven outward by the radiation pressure and fast stellar winds emanating from the exposed stellar core at their centers. The mechanics of mass ejection during the asymptotic giant branch phase involve multiple physical processes operating simultaneously across different regions of the stellar envelope. The primary driver is the pulsation-enhanced dust-driven wind mechanism, where the star's regular radial oscillations lift material to distances where temperatures drop below 1,500 Kelvin, allowing refractory compounds to condense into microscopic solid particles. These dust grains, typically composed of silicates in oxygen-rich stars or carbon compounds in carbon-rich stars, absorb and scatter the star's intense luminosity, transferring momentum from the radiation field to the surrounding gas. The coupling between dust and gas occurs through collisions, with the dust grains dragging the gas along as they are accelerated outward by radiation pressure. The mass loss rates during the superwind phase at the end of the asymptotic giant branch can reach extraordinary values of 10 to the -4 solar masses per year, meaning the star sheds the equivalent of Earth's mass every few hours. This intense outflow strips away the remaining hydrogen envelope over a timescale of only 10,000 to 100,000 years, far shorter than the millions of years the star spent on the asymptotic giant branch. The superwind creates a dense, slow-moving shell of material, expanding at velocities of 10 to 30 kilometers per second, carrying with it the products of nucleosynthesis dredged up from the stellar interior during thermal pulse events. As the envelope mass diminishes below the critical threshold of approximately 0.01 solar masses, the star undergoes a rapid transition in its fundamental structure. The hydrogen-burning shell, which has been the dominant energy source throughout the red giant phases, begins to weaken as its fuel supply dwindles. The stellar remnant contracts on a thermal timescale, its radius shrinking from several hundred solar radii to approximately Earth's radius over a period of 1,000 to 10,000 years. This contraction releases gravitational potential energy, causing the surface temperature to rise dramatically from the cool 3,000 Kelvin of the asymptotic giant branch to temperatures exceeding 100,000 Kelvin in the hottest planetary nebula central stars. The ionization of the ejected envelope begins when the central star's surface temperature exceeds approximately 25,000 Kelvin, at which point the star emits sufficient ultraviolet photons with energies above 13.6 electron volts to ionize hydrogen atoms. The ionization front propagates outward through the expanding shell at a rate determined by the balance between the flux of ionizing photons and the recombination rate of the gas. In a typical planetary nebula with a central star luminosity of several thousand solar luminosities and a gas density of 1,000 to 10,000 particles per cubic centimeter, the ionization front can travel at velocities of tens of kilometers per second, eventually catching up with and ionizing the entire visible nebula. The characteristic emission spectrum of planetary nebulae arises from the recombination and collisional excitation processes occurring in the ionized gas. When free electrons recombine with hydrogen ions, they cascade down through the energy levels, emitting photons at specific wavelengths, including the prominent hydrogen alpha line at 656.3 nanometers, which gives many planetary nebulae their distinctive red coloration. Collisional excitation of heavier elements, particularly oxygen, nitrogen, and neon, produces the forbidden emission lines that dominate the optical spectrum. The green glow characteristic of many planetary nebulae comes from the doubly ionized oxygen forbidden lines at 495.9 and 500.7 nanometers, transitions that are forbidden by quantum mechanical selection rules but occur readily in the extremely low-density nebular environment, where atoms can remain in excited states for extended periods without collisional de-excitation. The morphology of planetary nebulae displays remarkable diversity, ranging from simple spherical shells to complex bipolar structures with intricate internal features. This variety reflects the complex interplay of physical processes shaping the expanding gas, including the interaction between fast and slow winds, magnetic field effects, binary companion influences, and density variations in the circumstellar environment. The interacting stellar winds model explains many observed features through the collision between the fast, tenuous wind from the hot, central star, moving at velocities of 1,000 to 4,000 kilometers per second, and the slower, denser material ejected during the asymptotic giant branch phase. This interaction creates a hot bubble of shocked gas at temperatures exceeding 1 million Kelvin, bounded by a thin, dense shell that sweeps up the slower wind material. The Helix Nebula, located approximately 650 light-years from Earth in the constellation Aquarius, exemplifies the complexity of planetary nebula structure. Its apparent diameter of nearly half a degree on the sky corresponds to a physical extent of approximately 2.5 light-years, making it one of the largest and nearest planetary nebulae known. High-resolution observations reveal thousands of cometary knots, dense condensations of molecular gas and dust, with characteristic tadpole shapes pointing away from the central star. These knots, each containing roughly 1 Earth mass of material, represent regions where the advancing ionization front encounters density enhancements in the previously ejected envelope. The photoevaporation of these knots creates the distinctive cometary tails, streaming away from the central star at velocities of several tens of kilometers per second. The Ring Nebula in the constellation Lyra, perhaps the most famous planetary nebula visible from Earth, demonstrates the importance of viewing geometry in determining apparent structure. Long assumed to be a simple ring-shaped shell, detailed observations have revealed it to be a bipolar structure viewed nearly pole-on, with the bright ring representing the dense equatorial waste of an hourglass-shaped nebula. The central star, with a surface temperature of approximately 125,000 Kelvin, ionizes the surrounding gas, while itself appearing as a faint 15th magnitude point of light at the nebula's center. The expansion velocity of the main ring, measured through Doppler shifts of the emission lines, is approximately 20 kilometers per second, implying a kinematic age of roughly 7,000 years since the gas was ejected from the central star. Bipolar planetary nebulae, like the Butterfly Nebula in Scorpius, display extreme departures from spherical symmetry, with narrow waists and extended lobes stretching in opposite directions. The central star of the Butterfly Nebula has a surface temperature exceeding 200,000 Kelvin, making it one of the hottest stars known and indicating that the nebula is relatively young, with the central star still in the rapid heating phase of its post-asymptotic giant branch evolution. The bipolar morphology likely results from the presence of a dense equatorial disk, or torus, that collimates the fast stellar wind into the polar directions, though the origin of this disk remains debated. Possibilities include binary interactions, magnetic field effects, or rapid rotation of the progenitor star during the asymptotic giant branch phase. The chemical abundances measured in planetary nebulae provide crucial information about the nucleosynthesis occurring in their progenitor stars and the subsequent dredge-up processes that transported these products to the stellar surface. Carbon-rich planetary nebulae, where the carbon-to-oxygen ratio exceeds unity, indicate that their progenitors experienced efficient third dredge-up during thermal pulses, bringing freshly synthesized carbon from the helium-burning shell to the envelope. Nitrogen enrichment, particularly in more massive progenitors, results from hot bottom burning during the asymptotic giant branch phase, where temperatures at the base of the convective envelope exceed 40 million Kelvin, allowing the conversion of carbon to nitrogen through the carbon-nitrogen-oxygen cycle. The exposed core that remains after the planetary nebula disperses into the interstellar medium represents one of the most extraordinary objects in the universe, a stellar corpse supported not by the familiar pressure of hot gas, but by a quantum mechanical phenomenon that prevents further collapse. This white dwarf, typically containing roughly half the original mass of its progenitor star, compressed into a volume comparable to Earth, achieves densities that seem almost incomprehensible by terrestrial standards. A single teaspoon of white dwarf material would weigh approximately 5 to 10 metric tons, denser than any substance found naturally on our planet. The physics governing white dwarf structure emerges from the Pauli exclusion principle, one of the fundamental rules of quantum mechanics that forbids two fermions from occupying the same quantum state simultaneously. Electrons, being fermions, cannot be squeezed arbitrarily close together without violating this principle. As gravitational compression attempts to force electrons into increasingly confined spaces, they resist through what physicists call electron degeneracy pressure. This pressure depends not on temperature, as ordinary gas pressure does, but purely on density. A white dwarf could theoretically cool to absolute zero and still maintain its structural integrity against gravitational collapse, supported entirely by the quantum mechanical resistance of its electrons. The relationship between mass and radius in white dwarfs follows a counterintuitive pattern that distinguishes them from ordinary matter. While adding mass to a normal star causes it to expand, adding mass to a white dwarf causes it to shrink. This inverse relationship arises because increased gravitational compression forces electrons into higher momentum states, increasing the degeneracy pressure, but also allowing the material to occupy less volume. A white dwarf with half the mass of the Sun might have a radius of approximately 12,000 kilometers, while one approaching the maximum possible mass shrinks to perhaps 4,000 kilometers, barely larger than Mars. The internal structure of a newly formed white dwarf consists primarily of carbon and oxygen nuclei, the products of helium burning in the progenitor star's core, surrounded by a thin atmosphere of lighter elements. The carbon-oxygen core contains roughly 99% of the white dwarf's mass, arranged in a crystalline lattice at the highest densities. This crystallization process, which begins when the white dwarf cools to temperatures around 6,000 Kelvin in its interior, releases latent heat that temporarily slows the cooling rate. The phase transition from liquid to solid proceeds from the center outward as the star ages, eventually producing a cosmic diamond potentially thousands of kilometers in diameter. The thin outer layers of a white dwarf, comprising less than 1% of its total mass, determine its spectral classification and observable properties. Hydrogen atmosphere white dwarfs, designated DA in astronomical nomenclature, display strong hydrogen absorption lines and account for approximately 80% of observed white dwarfs. Their atmospheres, though containing only about 1/10,000th of the star's mass, completely dominate the spectrum because the underlying carbon-oxygen core remains hidden beneath this opaque layer. Helium atmosphere white dwarfs, classified as DB, lack hydrogen entirely, likely because gravitational settling has caused the heavier helium to sink below any residual hydrogen, or because the progenitor star lost its hydrogen envelope through particularly vigorous mass loss during the asymptotic giant branch phase. The surface gravity of a typical white dwarf exceeds that of the Sun by a factor of roughly 100,000, creating conditions where gravitational settling operates with remarkable efficiency. Heavy elements sink through the atmosphere on timescales of days to years, depending on the atmospheric composition and temperature. This rapid settling explains why white dwarf atmospheres appear so chemically pure, containing essentially only the lightest elements that float atop the denser material below. When heavier elements such as calcium, magnesium, or iron appear in white dwarf spectra, astronomers interpret this as evidence of recent accretion, often from asteroids or comets that wandered too close and were tidally disrupted. The cooling process that governs white dwarf evolution proceeds through several distinct phases, each dominated by different physical mechanisms. Immediately after formation, when surface temperatures exceed 100,000 Kelvin, the white dwarf radiates energy primarily through neutrino emission from its interior. These ghostly particles, produced by various weak nuclear processes in the dense plasma, escape directly without interacting with the overlying material, carrying away energy far more efficiently than photon radiation from the surface. This neutrino cooling phase lasts only a few million years, but reduces the interior temperature dramatically. As the white dwarf cools below approximately 25,000 Kelvin in its core, photon diffusion through the degenerate interior becomes the dominant energy transport mechanism. The thermal energy stored in the ionic lattice slowly leaks outward, eventually radiating from the surface as visible and infrared light. The cooling rate during this phase depends sensitively on the opacity of the thin, non-degenerate atmosphere, which acts as an insulating blanket controlling how rapidly heat escapes. Hydrogen atmospheres, being more opaque than helium atmospheres at equivalent temperatures, slow the cooling process, causing hydrogen atmosphere white dwarfs to appear younger than their helium atmosphere counterparts of the same actual age. The luminosity of a cooling white dwarf decreases steadily over billions of years, following a well-understood relationship that allows astronomers to use white dwarfs as cosmic chronometers. A white dwarf with a surface temperature of 25,000 Kelvin has typically been cooling for roughly 100 million years, while one that has faded to 5,000 Kelvin has been cooling for approximately 8 billion years. The oldest white dwarfs in the Milky Way's disk, with temperatures approaching 4,000 Kelvin and luminosities less than 1/10,000th that of the Sun, provide independent age estimates for our galaxy that agree remarkably well with other dating methods. Sirius B, the companion to the brightest star in Earth's night sky, serves as the prototype white dwarf and the first such object ever identified. With a mass of approximately 1 solar mass compressed into a volume slightly smaller than Earth, Sirius B achieves a density of roughly 2 million grams per cubic centimeter. Its surface temperature of approximately 25,000 Kelvin gives it a bluish-white color, though its tiny size renders it nearly invisible against the glare of its brilliant companion. The gravitational redshift of light escaping from Sirius B's intense gravitational field provided one of the earliest confirmations of general relativity, with spectral lines shifted toward longer wavelengths by approximately 80 kilometers per second equivalent velocity. The fate of these stellar remnants stretches toward infinity, a cooling process that will continue for timescales that dwarf the current age of the universe. Over trillions of years, white dwarfs will fade through the visible spectrum into the infrared, eventually becoming black dwarfs, objects so cold they emit essentially no radiation. No black dwarfs yet exist anywhere in the cosmos, as the universe at 14 billion years old remains far too young for even the oldest white dwarfs to have cooled to this final state. The transformation requires perhaps 10 to the 15th years, a quadrillion years, a span so vast that the stars themselves will have long since ceased forming before the first black dwarf emerges from the darkness. Yet not all white dwarfs face this eternal cooling into darkness. Some exist in binary systems where matter flows from a companion star, accumulating on the white dwarf surface in a process that fundamentally alters the remnant's destiny. This accumulation introduces a critical threshold, a mass boundary that determines whether a white dwarf continues its quiet existence or faces catastrophic destruction. This boundary, calculated by a young physicist in 1930, represents one of the most profound discoveries in stellar astrophysics. Subramanian Chandrasekhar, barely 20 years old, performed these calculations during a sea voyage from India to England. Working with the mathematics of electron degeneracy pressure and special relativity, he discovered something that initially shocked the astronomical community. The pressure that supports white dwarfs against gravitational collapse has a fundamental limit. As a white dwarf gains mass, the electrons supporting it must move faster and faster to provide sufficient pressure. but electrons cannot exceed the speed of light, approximately 300,000 kilometers per second. This relativistic constraint places an absolute ceiling on the mass that electron degeneracy pressure can support. The mathematics reveals this limit with remarkable precision. When a white dwarf approaches approximately 1.4 solar masses, the electrons in its core must move at velocities approaching the speed of light to maintain pressure equilibrium. At this point, the relationship between pressure and density changes fundamentally. In non-relativistic conditions, pressure increases proportionally to density raised to the 5/3 power. But as electrons become relativistic, this relationship weakens to density raised to only the 4/3 power. The pressure simply cannot increase fast enough to counterbalance the growing gravitational force. This critical mass, known as the Chandrasekhar limit, equals precisely 1.44 solar masses when calculated for a white dwarf composed primarily of carbon and oxygen. The exact value depends slightly on composition, ranging from about 1.38 solar masses for iron-rich cores to 1.46 solar masses for helium-dominated objects. But for the typical carbon-oxygen white dwarfs produced by solar mass stars, the canonical value of 1.4 solar masses serves as the definitive boundary between stability and collapse. The physics underlying this limit emerges from the Pauli exclusion principle, the quantum mechanical rule that forbids two fermions from occupying identical quantum states. Electrons, being fermions, must each occupy a unique combination of position and momentum. In the incredibly dense environment of a white dwarf, where matter reaches densities of approximately 1 million grams per cubic centimeter, the electrons are squeezed into the smallest possible volume. They respond by occupying higher and higher momentum states, creating the degeneracy pressure that supports the star. Consider a white dwarf with a mass of 1 solar mass, a typical remnant from a star like our Sun. Its radius measures approximately 6,000 kilometers, comparable to Earth but containing 330,000 times more mass. The central density reaches roughly 10 million grams per cubic centimeter, and the central pressure approaches 10 to the 23rd pascals. The electrons at the core move at velocities around 1,000 kilometers per second, fast, but still well below relativistic speeds. This white dwarf exists in comfortable equilibrium, its electron degeneracy pressure easily balancing gravitational compression. Now imagine adding mass to this white dwarf, perhaps through accretion from a binary companion. As the total mass increases toward 1.2 solar masses, the gravitational force intensifies, compressing the core to higher densities. The radius actually shrinks counterintuitively from 6,000 kilometers to perhaps 5,000 kilometers. The central density climbs toward 100 million grams per cubic centimeter, and the electrons must move faster, reaching tens of thousands of kilometers per second, a significant fraction of light speed. The relationship between mass and radius for white dwarfs follows a peculiar inverse pattern. More massive white dwarfs are actually smaller than less massive ones, a direct consequence of the degeneracy pressure equation of state. A white dwarf of half a solar mass might have a radius of 10,000 kilometers, while one approaching the Chandrasekhar limit shrinks to barely 2,000 kilometers. This compression continues until the electrons become fully relativistic. at which point no stable configuration exists. At one point, 3 solar masses, the white dwarf has contracted to approximately 3,000 kilometers radius. The central density exceeds 1 billion grams per cubic centimeter, and the electrons move at velocities exceeding 100,000 kilometers per second, more than 30% the speed of light. The star teeters on the edge of stability, its structure increasingly sensitive to any additional mass. The gravitational binding energy has grown to approximately 10 to the 44 joules, comparable to the energies that will be released if the star eventually collapses. The approach to the Chandrasekhar limit creates conditions ripe for thermonuclear ignition. As the core compresses and heats, the carbon and oxygen nuclei experience temperatures exceeding several hundred million Kelvin. Unlike the helium flash in red giant cores, where degeneracy prevented expansion and temperature regulation, the carbon ignition in a near Chandrasekhar white dwarf triggers a runaway thermonuclear explosion. The fusion reactions release energy faster than the star can respond, converting a significant fraction of the stellar mass to nickel-56 and other iron peak elements within mere seconds. This thermonuclear runaway produces a Type 1a supernova, one of the most luminous events in the universe. The explosion releases approximately 10 to the 44 joules of energy, with about 1% emerging as visible light. At peak brightness, a Type 1a supernova can outshine its entire host galaxy, reaching absolute magnitudes of -19, equivalent to 5 billion solar luminosities. The remarkable consistency of these explosions, a direct consequence of the fixed Chandrasekhar mass triggering the detonation, makes them invaluable as standard candles for measuring cosmic distances. The uniformity arises because all Type 1a supernovae begin from essentially identical conditions. A white dwarf at 1.4 solar masses has a specific central density, a specific temperature profile, and a specific composition. The nuclear burning proceeds through the same sequence regardless of the white dwarf's history or location in the universe. Approximately half a solar mass of nickel-56 forms in each explosion, and the radioactive decay of this isotope, first to cobalt-56 with a half-life of 6 days, then to stable iron-56 with a half-life of 77 days, powers the supernova light curve for months after the initial detonation. The Chandrasekhar limit also determines the fate of white dwarfs that do not explode. Those that remain below this mass boundary continue their eternal cooling, eventually becoming black dwarfs over quadrillions of years. But the limit itself represents more than just a threshold for explosion. It marks the boundary where electron degeneracy pressure fails as a support mechanism, where the quantum mechanical properties of electrons can no longer resist gravity's inexorable pull. Beyond this limit, if a stellar core somehow avoided thermonuclear detonation, gravity would compress the matter to even higher densities. The electrons would be forced to combine with protons through inverse beta decay, producing neutrons and neutrinos. The neutrinos would escape, carrying away energy, while the neutrons would form a new type of degenerate matter. This neutron degeneracy pressure can support masses up to approximately 2 to 3 solar masses, creating neutron stars rather than white dwarfs. The precision of the Chandrasekhar calculation, confirmed by decades of observations and refined theoretical work, stands as one of the triumphs of 20th century astrophysics. White dwarfs observed throughout the galaxy cluster below this limit, with the most massive examples reaching 1.3 or 1.35 solar masses. None exceed the theoretical boundary, a powerful confirmation that the physics of electron degeneracy and special relativity correctly describes these stellar remnants. The physics that governs white dwarf stability finds its counterpart in the lives of far more massive stars, where the relentless crush of gravity drives nuclear fusion to extraordinary extremes. Stars born with masses exceeding 8 solar masses follow evolutionary paths fundamentally different from their smaller siblings, burning through their nuclear fuel with furious intensity and developing internal structures of remarkable complexity. These stellar giants, though rare compared to the countless red and yellow dwarfs that populate the galaxy, play outsized roles in cosmic chemistry, forging the heavy elements that will eventually become planets, oceans, and living organisms. A massive star begins its life much like any other, collapsing from a molecular cloud and igniting hydrogen fusion in its core. But the similarities end quickly. Where a solar mass star might burn hydrogen for 10 billion years, a star of 20 solar masses exhausts its core hydrogen supply in merely 8 million years. A star of 40 solar masses completes this phase in just 3 million years. The difference arises from the cubic relationship between mass and luminosity for massive stars. Doubling a star's mass increases its energy output by roughly 8 to 16 times, depending on the exact mass range. This prodigious luminosity demands correspondingly rapid fuel consumption, setting these stellar giants on accelerated paths towards their ultimate fates. The core temperatures in massive stars reach values that dwarf those found in solar-type stars. While the Sun's center maintains approximately 15 million Kelvin, the core of a 20 solar mass star operates at 40 million Kelvin or higher. At these temperatures, the CNO cycle dominates hydrogen fusion rather than the proton-proton chain that powers smaller stars. Carbon, nitrogen, and oxygen nuclei serve as catalysts, facilitating the conversion of hydrogen to helium through a series of proton captures and beta decays. The reaction rate of the CNO cycle depends on temperature raised to the 16th or 17th power, making it extraordinarily sensitive to core conditions. A modest temperature increase produces dramatic increases in energy generation, concentrating the fusion reactions into a smaller, hotter central region. This intense energy production creates steep temperature gradients that drive powerful convection throughout much of the stellar interior. Unlike the Sun, where the core remains radiative and stable, massive stars develop convective cores that churn and mix nuclear-processed material. Fresh hydrogen continuously cycles into the burning region, while helium ash distributes throughout the convective zone. This mixing extends the hydrogen-burning phase slightly and homogenizes the core composition. The convective boundary marks a sharp transition, beyond which lies a radiative envelope that transports energy outward through photon diffusion. When hydrogen exhaustion finally occurs, the core contracts and heats, following the same gravitational imperative that governs all stellar evolution. But in massive stars, this contraction proceeds more smoothly than in their lower mass counterparts. The core never becomes electron degenerate during these intermediate phases, because the temperatures rise quickly enough to ignite the next fusion stage before degeneracy can establish itself. Helium burning begins at approximately 100 million Kelvin, converting helium to carbon through the triple alpha process. In a 20 solar mass star, this phase lasts roughly 1 million years, a dramatic acceleration from the hydrogen-burning timescale. The triple alpha process produces carbon-12, but at the elevated temperatures found in massive star cores, a significant fraction of this carbon captures additional helium nuclei to form oxygen-16. The ratio of carbon to oxygen produced depends sensitively on the core temperature and the nuclear reaction rates involved. Typical massive stars produce roughly equal amounts of carbon and oxygen by mass during helium burning, though this ratio varies with stellar mass and the still uncertain rate of the carbon-12 plus helium-4 reaction. These two elements, carbon and oxygen, rank among the most abundant in the universe precisely because of their copious production in massive stars. As the helium supply dwindles, the core contracts once more, and temperatures climb toward 600 million Kelvin. At this threshold, carbon nuclei begin fusing with each other, producing a variety of products including neon-20, sodium-23, and magnesium-24, along with protons, neutrons, and alpha particles. Carbon burning in a 20 solar mass star lasts approximately 1,000 years, a mere eye blink in stellar terms. The energy released supports the star against gravity, but the accelerating pace of evolution becomes unmistakable. Each successive burning stage proceeds faster than the last, driven by the increasing energy losses from neutrino emission. Neutrinos, those ghostly particles that interact so weakly with matter, become increasingly important as core temperatures rise. At the temperatures characteristic of carbon burning and beyond, thermal neutrino production through processes like pair annihilation and plasmon decay, removes energy directly from the stellar core. Unlike photons, which must random walk through the stellar interior over thousands of years, neutrinos escape immediately, carrying away energy that might otherwise support the star. This neutrino luminosity eventually exceeds the photon luminosity by factors of thousands, draining the core and accelerating its evolution. Following carbon exhaustion, neon burning commences at approximately 1.2 billion Kelvin. This stage proceeds through photodisintegration, where high-energy photons break apart neon-20 nuclei, releasing alpha particles that are then captured by other neon nuclei to form magnesium-24. Neon burning lasts only a few years in a typical massive star. The core continues its relentless contraction and heating, reaching 1.5 billion Kelvin where oxygen burning ignites. Oxygen nuclei fuse to produce silicon-28, sulfur-32, and various other intermediate mass elements. This phase persists for perhaps 6 months to a year. The stellar interior now develops the characteristic onion shell structure that defines advanced massive star evolution. At the very center lies the active burning shell, surrounded by concentric layers of progressively lighter elements. Moving outward from the core, one encounters shells of silicon and sulfur, then oxygen and neon, then carbon, then helium, and finally the hydrogen-rich envelope. Each shell represents the ashes of a previous burning stage, and several of these shells may be actively fusing simultaneously. The silicon-burning shell produces iron group elements, while the oxygen shell above it continues converting oxygen to silicon, and the carbon shell above that processes carbon to neon and magnesium. Silicon burning represents the final chapter of nuclear fusion in a massive star. At temperatures exceeding 3 billion Kelvin, silicon nuclei undergo a complex series of photodisintegration and capture reactions that gradually build up nuclei toward the iron peak. This process, sometimes called nuclear statistical equilibrium, does not proceed through simple fusion of silicon nuclei. Instead, high-energy photons break apart silicon and other intermediate nuclei, releasing protons, neutrons, and alpha particles that are then captured by other nuclei. The system reaches a quasi-equilibrium state, where the composition shifts steadily toward iron-56 and nickel-56, the most tightly bound nuclei in nature. Silicon burning in the core of a massive star lasts approximately 1 day. In those final 24 hours, the star produces an iron core of roughly 1.4 solar masses, the same Chandrasekhar mass that limits white dwarf stability. But unlike the gradual cooling that awaits isolated white dwarfs, this iron core faces immediate catastrophe. Iron cannot release energy through fusion. Its binding energy per nucleon sits at the peak of the curve, meaning that both fusion and fission of iron group nuclei require energy input rather than providing energy output. The core has reached a dead end, supported only by electron degeneracy pressure against the crushing weight of the overlying stellar layers. The outer layers of the star remain largely unaware of the drama unfolding in the core. The stellar surface, now expanded to red supergiant dimensions spanning hundreds of solar radii, continues radiating energy into space. The hydrogen envelope, if it still exists, burns placidly in a shell far removed from the central crisis. The timescales of the outer layers, measured in thousands of years for significant changes, cannot respond to events occurring over hours in the core. This disconnect between surface and center means that the star appears essentially unchanged to external observers, even as its heart prepares for collapse. The silicon-burning phase that now dominates the stellar core represents the final, desperate attempt of nuclear fusion to stave off gravitational collapse. At temperatures exceeding 3 billion Kelvin, silicon nuclei possess sufficient thermal energy to overcome the immense Coulomb barrier that normally prevents their interaction. The process unfolds not through direct fusion of silicon with silicon, but through a complex network of photodisintegration and alpha capture reactions that gradually build heavier nuclei toward the iron peak. At these extreme temperatures, the radiation field becomes so intense that high-energy gamma-ray photons can shatter atomic nuclei apart, liberating alpha particles, protons, and neutrons. Silicon-28 nuclei absorb these freed particles, climbing the nuclear ladder through sulfur-32, argon-36, calcium-40, titanium-44, chromium-48, and finally to iron-56 and nickel-56. The process resembles a nuclear equilibrium where creation and destruction occur simultaneously, with the balance gradually shifting toward the most stable configurations. Iron-56 and nickel-56 represent the peak of the binding energy curve, the most tightly bound nuclei in existence, with approximately 8.8 million electron volts of binding energy per nucleon. The silicon-burning core occupies a remarkably small volume, perhaps only 1,500 kilometers in radius, yet contains approximately 1.5 solar masses of material compressed to densities approaching 10 billion kilograms per cubic meter. The temperature gradient across this region spans from 3 billion Kelvin at the center to roughly 2 billion Kelvin at the outer boundary of active silicon fusion. Energy production rates during this phase reach staggering values, with the core generating more energy per second than the entire rest of the star has produced throughout its multi-million-year lifetime on the main sequence. Yet this prodigious energy generation cannot last. Silicon burning consumes its fuel with extraordinary rapidity, exhausting the available silicon in approximately 1 day. Some massive stars complete this phase in as little as 18 hours, a mere heartbeat compared to the millions of years spent fusing hydrogen or the thousands of years burning helium. The brevity of this phase reflects the fundamental inefficiency of silicon burning, which releases only about 1/10 the energy per unit mass compared to hydrogen fusion, while the star's luminosity demands remain essentially unchanged. As silicon depletes, the core composition shifts inexorably toward iron group elements. Nickel-56, produced in abundance during silicon burning, undergoes radioactive decay with a half-life of 6.1 days, transforming first into cobalt-56 and then into stable iron-56. The growing iron core represents a fundamental crisis in stellar physics, for iron fusion cannot proceed exothermically. Attempting to fuse iron nuclei requires energy input rather than providing energy output, a consequence of iron's position at the peak of the nuclear binding energy curve. The iron core grows through continued silicon shell burning, accumulating mass like sand filling an hourglass. When the core mass approaches the Chandrasekhar limit of approximately 1.4 solar masses, electron degeneracy pressure begins to falter. At densities exceeding 10 billion kilograms per cubic meter and temperatures above 5 billion Kelvin, two processes accelerate the core's demise. Electron capture onto iron group nuclei removes the very electrons providing degeneracy support, while photodisintegration of iron nuclei absorbs thermal energy that would otherwise contribute to pressure support. The electron capture process transforms protons within iron nuclei into neutrons, releasing neutrinos that escape the core at nearly the speed of light. Each captured electron removes 1 unit of degeneracy pressure support, while simultaneously reducing the number of particles available to provide thermal pressure. The reaction iron-56 plus electron yields manganese-56 plus electron neutrino, proceeds at rates that increase exponentially with temperature and density, creating a runaway feedback loop. Photodisintegration compounds this catastrophe. Gamma-ray photons with energies exceeding 7.6 million electron volts can shatter iron-56 nuclei into 13 helium-4 nuclei and 4 neutrons, absorbing approximately 124 million electron volts of energy in the process. This energy absorption cools the core, reducing thermal pressure support precisely when the star needs it most. The destruction of iron nuclei that required billions of years of stellar evolution to construct occurs in fractions of a second. The core temperature continues rising despite this energy drain, driven by gravitational compression as the star's own weight bears down upon the failing support structure. At temperatures approaching 10 billion Kelvin, even helium nuclei undergo photodisintegration, breaking apart into free protons and neutrons. Each helium nucleus destroyed absorbs 28.3 million electron volts, further accelerating the thermal catastrophe. The core enters a state of negative feedback where compression leads to cooling through photodisintegration, which reduces pressure, which causes further compression. The timescale of core collapse accelerates dramatically. What began as a gradual accumulation of iron over hours now transitions to catastrophic implosion over milliseconds. The inner core, comprising roughly 0.6 solar masses of material, begins falling inward at velocities approaching 1/4 the speed of light. The outer core follows, creating an infalling mass flux of approximately 1 solar mass per second. No process in the universe can halt this collapse through normal pressure support. The density of the collapsing core increases by factors of millions within fractions of a second. Material that occupied a volume comparable to Earth compresses toward dimensions measured in tens of kilometers. At densities exceeding 100 trillion kilograms per cubic meter, atomic nuclei begin merging together, their individual identities dissolving into a continuous sea of nuclear matter. The distinction between separate iron nuclei vanishes as the entire core approaches the density of an atomic nucleus itself. Neutrino production during this collapse reaches extraordinary levels. The core generates approximately 10 to the 58th power neutrinos within the first second of collapse, carrying away roughly 3 times 10 to the 46th joules of energy. This neutrino luminosity exceeds the combined electromagnetic output of every star in the observable universe. Yet these ghostly particles pass through the overlying stellar material almost unimpeded. Only at the extreme densities of the collapsing core do neutrinos begin experiencing significant interactions with matter. The outer stellar envelope remains suspended above this collapsing core, temporarily unaware of the catastrophe below. The speed of sound in stellar material, approximately 1,000 kilometers per second in the outer layers, cannot transmit information about the core collapse faster than the collapse itself proceeds. The surface of the red supergiant, still spanning hundreds of solar radii, continues radiating starlight into space as if nothing unusual were occurring. The disconnect between the serene stellar surface and the violent core implosion represents one of the most dramatic contrasts in astrophysics. Within the collapsing core, the temperature exceeds 50 billion Kelvin as compression continues. At these conditions, thermal radiation consists primarily of electron-positron pairs, created spontaneously from the intense photon field. The core becomes opaque even to neutrinos as densities approach and exceed nuclear density of approximately 2.3 times 10 to the 17th kilograms per cubic meter. Neutrinos that previously escaped freely now find themselves trapped within the collapsing material, their mean free path shrinking to mere meters. The inner core reaches nuclear density and experiences a dramatic stiffening as the strong nuclear force begins resisting further compression. This nuclear equation of state halts the collapse of the innermost material, which rebounds slightly outward like a compressed spring. The infalling outer core, still plunging inward at tens of thousands of kilometers per second, collides with this rebounding inner core, generating a powerful shock wave that propagates outward through the still falling material. The shock wave born from this collision carries enormous energy, approximately 3 times 10 to the 46 joules. Yet this energy proves insufficient to overcome the ram pressure of the material, still cascading inward at velocities exceeding 70,000 kilometers per second. Within milliseconds of its formation, the shock wave stalls at a radius of roughly 100 to 200 kilometers from the center, its outward momentum exhausted against the relentless infall of the outer core. This stalled shock represents a critical juncture in the collapse process. Behind the shock front, temperatures exceed 10 billion Kelvin, hot enough to photodisintegrate the iron nuclei that took millions of years to forge. Each iron nucleus that crosses the shock absorbs approximately 8.8 mega-electron volts of energy as it shatters into free protons and neutrons, draining energy from the shock wave at a rate of nearly 10 to the 52 ergs per second. The very elements that signaled the end of fusion now actively work to prevent the explosion that might disperse them into space. The proto-neutron star, forming at the center of this chaos, represents matter in conditions found nowhere else in the observable universe, except during the first microseconds after the Big Bang. Its density exceeds 3 times 10 to the 17th kilograms per cubic meter, meaning a teaspoon of this material would weigh approximately 500 million metric tons on Earth's surface. The temperature at its center reaches 30 to 50 billion Kelvin, hot enough that thermal radiation peaks in the gamma-ray spectrum at energies exceeding several mega-electron volts. Within this proto-neutron star, the process of neutronization accelerates dramatically. Electrons, squeezed into ever smaller volumes, find it energetically favorable to combine with protons through inverse beta decay, producing neutrons and electron neutrinos. The reaction rate depends on the 6th power of the temperature and the square of the electron Fermi energy, both of which increase rapidly as compression continues. Within the first few hundred milliseconds, the electron fraction drops from approximately 0.42 to below 0.35, releasing a flood of electron neutrinos that carry away lepton number from the collapsing core. The neutrino luminosity during this phase defies comprehension. The proto-neutron star radiates approximately 3 times 10 to the 53 ergs in neutrinos over a period of roughly 10 seconds, a luminosity that briefly exceeds the combined electromagnetic output of every star in the observable universe. These neutrinos carry away the gravitational binding energy released as the core contracts from a radius of several thousand kilometers to merely 20 kilometers, converting gravitational potential energy into neutrino kinetic energy with remarkable efficiency. The neutrino spectrum during collapse reflects the extreme conditions within the proto-neutron star. Electron neutrinos emerge with average energies of approximately 12 mega-electron volts, while electron antineutrinos carry slightly higher energies near 15 mega-electron volts. The mu and tau neutrinos produced through thermal pair creation rather than charged current reactions emerge with the highest average energies of approximately 18 mega-electron volts. These energy differences arise from the different opacity each neutrino flavor experiences as it diffuses outward through the dense nuclear matter. The neutrino sphere, the surface from which neutrinos can finally escape freely, lies at a radius of approximately 40 to 60 kilometers, where the density drops to roughly 10 to the 12th kilograms per cubic meter. This surface is not sharp, but rather represents a gradual transition where the neutrino mean free path increases from meters to infinity over a distance of several kilometers. The temperature at the neutrino sphere reaches approximately 4 to 5 mega-electron volts, or roughly 50 billion Kelvin, setting the characteristic energy scale for the escaping neutrinos. Between the stalled shock and the neutrino sphere lies a region of intense activity known as the gain region. Here, a small fraction of the outward streaming neutrinos deposit their energy through charged current absorption on free nucleons. When an electron neutrino encounters a neutron, it can convert it to a proton while transferring its energy to the resulting electron. Similarly, electron antineutrinos can convert protons to neutrons. These reactions heat the material in the gain region at a rate of approximately 10 to the 51 ergs per second, potentially providing the energy needed to revive the stalled shock. The competition between neutrino heating in the gain region and neutrino cooling below it determines whether the shock can be revived. The heating rate scales with the square of the neutrino luminosity and inversely with the square of the radius, while the cooling rate depends on the sixth power of the local temperature. At radii between approximately 60 and 150 kilometers, heating dominates, creating a reservoir of thermal energy that can potentially drive the shock outward. Convection plays a crucial role in this energy transfer. The gain region is convectively unstable because neutrino heating creates an entropy gradient that increases outward, opposite to the direction required for stability. Hot, buoyant plumes rise toward the shock, while cooler material sinks toward the neutrino sphere, creating a turbulent flow pattern that enhances the efficiency of neutrino energy deposition. Three-dimensional simulations reveal that this convection develops characteristic length scales of tens of kilometers, with velocities reaching thousands of kilometers per second. The standing accretion shock instability, known as SASY, introduces additional complexity to the post-bounce dynamics. This instability causes the shock front to oscillate in non-spherical modes, sloshing back and forth with periods of approximately 20 to 30 milliseconds. The dominant mode typically involves dipolar or quadrupolar deformations, with the shock radius varying by factors of 2 or more between different angular directions. These oscillations can help channel neutrino energy into the shock more efficiently by creating asymmetric heating patterns. The interplay between convection and SASY creates a highly turbulent environment behind the stalled shock. Magnetic fields, initially weak, can be amplified by differential rotation and turbulent dynamo action to strengths exceeding 10 to the 15 Gauss in localized regions. These fields remain dynamically unimportant for most core collapse supernovae, but may play crucial roles in the most rapidly rotating progenitors, potentially driving magnetically powered jets along the rotation axis. The timescale for shock revival, if it occurs, spans roughly 100 to several hundred milliseconds after bounce. During this interval, The shock radius hovers between 100 and 200 kilometers, neither advancing significantly nor retreating to the proto-neutron star surface. The outcome depends sensitively on the progenitor structure, the nuclear equation of state, and the neutrino transport, making core collapse supernovae among the most challenging problems in computational astrophysics. The mass accretion rate through the shock determines the ram pressure that the shock must overcome. For typical massive star progenitors, this rate begins at several solar masses per second immediately after bounce and decreases as the shock works its way through the density profile of the collapsing star. When the accretion rate drops sufficiently, typically below approximately 0.1 solar masses per second, the neutrino heating can finally overcome the ram pressure and the shock begins its outward journey. The moment of shock revival marks the transition from implosion to explosion. The shock accelerates outward, sweeping up the remaining infalling material and reversing its motion. Behind the shock, the expansion cools the material rapidly, freezing in the nuclear composition established during the brief high-temperature phase. Ahead of the shock, the stellar envelope remains unaware of the catastrophe unfolding at its center, still falling inward at velocities set by the original gravitational collapse. The revived shock wave now races outward through the stellar envelope at velocities exceeding 30,000 kilometers per second, a wall of compressed matter and radiation that will ultimately tear the star apart. This explosion, classified as a Type II supernova, derives its name from the hydrogen lines visible in its spectrum, evidence that the massive star retained its outer hydrogen envelope until the moment of its death. The physics driving this explosion represents one of the most complex phenomena in astrophysics, where neutrino transport, nuclear reactions, hydrodynamic instabilities, and relativistic gravity all interact on timescales measured in milliseconds. The neutrinos that ultimately power this explosion carry away approximately 99% of the gravitational binding energy released during core collapse. The total energy liberated when the iron core compresses into a neutron star reaches approximately 3 × 10⁴ joules, a quantity so vast that it exceeds the total energy output of the Sun over its entire 10 billion-year main sequence lifetime by a factor of several hundred. Of this enormous energy release, only about 1%, roughly 3 × 10⁴ joules, goes into the kinetic energy of the explosion itself. The remaining energy streams away as neutrinos, invisible messengers that pass through the stellar envelope as if it were transparent glass. The detection of neutrinos from supernova 1987A in the Large Magellanic Cloud provided direct confirmation of this theoretical picture. On February 23, 1987, approximately 3 hours before the optical brightening became visible, neutrino detectors in Japan, the United States, and the Soviet Union recorded a brief burst of neutrino interactions. The Kamiokande 2 detector in Japan observed 11 neutrino events over a span of 13 seconds. The IMB detector in Ohio recorded 8 events over approximately 6 seconds. These 20-odd neutrinos, captured from a supernova located 168,000 light-years away, represented the first direct observation of the neutrino burst predicted by core collapse theory. The energies of the detected neutrinos ranged from approximately 7 to 40 million electron volts, consistent with thermal emission from matter at temperatures near 50 billion Kelvin. The total number of neutrinos emitted by the supernova exceeded 10 to the 58th power, yet the enormous distance and the tiny interaction cross-section of neutrinos with matter meant that only this handful reached our detectors. The brief duration of the neutrino burst, lasting approximately 10 seconds, matched theoretical predictions for the cooling time of the newly formed neutron star as it radiated away its thermal energy. As the shock wave propagates outward through the stellar envelope, it encounters layers of progressively lighter elements, each representing a previous stage of nuclear burning. The shock first traverses the silicon and oxygen shells, where temperatures behind the shock front briefly exceed 5 billion Kelvin. At these temperatures, nuclear reactions proceed rapidly, synthesizing new elements through explosive nucleosynthesis. Silicon burns to nickel-56 in a matter of seconds, producing approximately 0.07 solar masses of this radioactive isotope in a typical Type II supernova. This nickel-56 will later decay to cobalt-56 and then to stable iron-56, powering the optical light curve of the supernova for months after the initial explosion. The passage of the shock through the oxygen-rich layers produces additional nucleosynthesis, creating elements from silicon through calcium. The peak temperatures reached during shock passage determine which nuclear reactions can proceed, with higher temperatures enabling the synthesis of heavier elements. Behind the shock, the rapid expansion causes temperatures to drop precipitously, freezing the nuclear composition at values determined by the brief high-temperature phase. This explosive nucleosynthesis contributes significantly to the galactic inventory of intermediate mass elements, complementing the hydrostatic nucleosynthesis that occurred during the star's lifetime. The hydrodynamic evolution of the expanding shock reveals complex three-dimensional structure that develops from the initial asymmetries present during shock revival. The standing accretion shock instability and neutrino-driven convection that operated during the stalled shock phase leave their imprint on the explosion geometry. Observations of supernova remnants consistently show departures from spherical symmetry, with clumpy ejecta distributions and high-velocity knots of material that suggest the explosion itself was inherently asymmetric. The Cassiopeia A supernova remnant, located approximately 11,000 light-years from Earth, provides a detailed laboratory for studying these asymmetries. X-ray observations revealed that the iron-rich ejecta, which originated from the deepest layers of the explosion, have been propelled outward faster than the silicon and sulfur layers that initially lay above them. This inversion of the expected layering suggests that powerful jets or plumes of neutrino-heated material punched through the overlying shells during the explosion, carrying the innermost ejecta to the outermost regions of the remnant. The optical light curve of a Type II supernova follows a characteristic pattern determined by the interplay of shock heating, radioactive decay, and photon diffusion. The initial flash of light occurs when the shock wave breaks through the stellar surface, releasing the radiation trapped behind the shock front. This shock breakout produces a brief pulse of ultraviolet and X-ray emission lasting only minutes to hours, depending on the radius of the progenitor star. For a red supergiant with a radius of several hundred solar radii, the shock requires approximately 1 day to traverse the stellar envelope after revival, and the breakout flash reaches luminosities exceeding 10 billion solar luminosities for a brief period. Following shock breakout, the expanding ejecta cool rapidly as they expand into the surrounding vacuum. The optical luminosity initially declines as the photosphere recedes through the cooling ejecta. However, the recombination of ionized hydrogen provides an additional energy source that sustains the luminosity during the plateau phase. As the ejecta cool below approximately 6,000 Kelvin, hydrogen atoms recombine from their ionized state, releasing the ionization energy as optical photons. This recombination wave moves inward through the ejecta in mass coordinates, while the ejecta themselves expand outward, maintaining a roughly constant photospheric temperature and luminosity for approximately 100 days. The duration of the plateau phase depends on the mass of the hydrogen envelope and the explosion energy. More massive envelopes contain more hydrogen available for recombination, extending the plateau duration. Higher explosion energies cause more rapid expansion, which accelerates the cooling and shortens the plateau. Typical Type 2P supernovae, where the P denotes plateau, maintain luminosities of approximately 10 to the 42 ergs per second for 80 to 120 days before the plateau ends and the luminosity drops sharply. After the plateau phase, the light curve enters the radioactive tail, where the luminosity is powered entirely by the decay of nickel-56 and its daughter product cobalt-56. Nickel-56 decays to cobalt-56 with a half-life of 6.1 days, emitting gamma rays that deposit their energy in the expanding ejecta. Cobalt-56 subsequently decays to stable iron-56 with a half-life of 77.3 days, and this longer-lived isotope dominates the energy input during the tail phase. The exponential decline of the light curve during this phase, with a characteristic time scale matching the cobalt-56 half-life, provides direct evidence for the radioactive power source. The gamma rays produced by radioactive decay must interact with the ejecta to convert their energy into optical photons. In the early phases, when the ejecta are dense, the gamma rays are efficiently absorbed and thermalized. As the ejecta expand and thin, an increasing fraction of gamma rays escape without depositing their energy, causing the light curve to decline faster than the radioactive decay rate alone would predict. Observations of this gamma ray leakage provide constraints on the distribution of nickel-56 within the ejecta and the total mass of the expanding material. The velocities of the expanding ejecta span a wide range, from a few hundred kilometers per second for the slowest material near the mass, cut to over 10,000 kilometers per second for the fastest outer layers. Spectroscopic observations reveal these velocities through the Doppler shifts of absorption and emission lines. The hydrogen lines that define Type 2 supernovae show velocities of 8 to 12,000 kilometers per second during the plateau phase, while heavier elements synthesized deeper in the explosion show progressively lower velocities consistent with their origin in the inner ejecta. The innermost regions of this expanding debris cloud conceal an object of almost incomprehensible density, a remnant forged in the final moments of core collapse when the relentless crush of gravity compressed matter beyond any state found elsewhere in the universe. This neutron star, born from the catastrophic implosion of an iron core, contains roughly 1.5 times the mass of our Sun, packed into a sphere merely 20 kilometers across. If one could somehow transport a teaspoon of neutron star material to Earth, it would weigh approximately 6 billion tons, more than the combined mass of every human being who has ever lived, multiplied by a factor of nearly 1,000. The density at the center of a neutron star reaches values of approximately 1 billion tons per cubic centimeter, a figure so extreme that ordinary intuitions about matter completely fail. At these densities, individual atoms cannot exist in any recognizable form. The electron shells that normally surround atomic nuclei have been crushed inward, forced by gravitational pressure to combine with protons through a process called inverse beta decay. Each proton captures an electron and transforms into a neutron while releasing a neutrino, the same process that generated the neutrino burst powering the supernova explosion. The result is matter composed almost entirely of neutrons, packed together at densities comparable to the atomic nucleus itself. The surface gravity of a neutron star exceeds that of Earth by a factor of approximately 200 billion. An object falling from a height of 1 meter would strike the surface at a velocity of roughly 2 million meters per second, releasing energy equivalent to a small nuclear weapon. This extreme gravitational field bends light so severely that an observer could theoretically see portions of the neutron star's far side, as photons traveling nearly parallel to the surface curve around the star. Approximately 75% of the total surface area becomes visible from any single vantage point, a geometric impossibility for any object with weaker gravity. The internal structure of a neutron star divides into distinct layers, each governed by different physical processes. The outermost layer, a thin atmosphere perhaps a centimeter thick, consists of hydrogen, helium, or heavier elements depending on the star's history of accretion. Below this lies a solid crust approximately 1 kilometer thick, composed of atomic nuclei arranged in a crystalline lattice and embedded in a sea of free electrons. The nuclei in this crust become increasingly neutron-rich with depth, as the growing pressure forces more and more inverse beta decay reactions. At a depth of roughly 1 kilometer, the pressure reaches approximately 4 times 10 to the 29th pascals, and the neutron-rich nuclei begin to dissolve. The boundary between the solid crust and the liquid interior marks a phase transition where nuclear matter transforms from discrete nuclei into a continuous fluid of neutrons, with a small admixture of protons and electrons. This transition region may contain exotic structures called nuclear pasta, where the competition between nuclear attraction and Coulomb repulsion creates shapes resembling spaghetti, lasagna, and other pasta forms at different densities. The outer core extends from the base of the crust to approximately half the neutron star's radius, containing a superfluid of neutrons interpenetrated by a superconducting fluid of protons. These quantum states arise because the temperature of a neutron star, though reaching hundreds of millions of Kelvin at birth, remains far below the critical temperature for neutron superfluidity. approximately 500 million Kelvin. In this superfluid state, neutrons pair together and flow without viscosity, while proton pairs carry electrical current without resistance. The superfluid nature of neutron star interiors produces observable consequences through a phenomenon called pulsar glitches. As a neutron star spins, its solid crust gradually slows due to magnetic braking, but the superfluid interior, decoupled from the crust, maintains its rotation. Periodically, angular momentum transfers suddenly from the faster spinning superfluid to the slower crust, producing an abrupt increase in the star's rotation rate. The Vela pulsar has exhibited over 20 such glitches since observations began, each increasing its spin frequency by roughly 1 part in a million before the gradual slowdown resumes. The inner core of a neutron star, occupying the central few kilometers, remains one of the most uncertain regions in all of astrophysics. At densities exceeding 5 times the nuclear saturation density, the behavior of matter depends on the strong nuclear force at energy scales inaccessible to terrestrial experiments. Some theoretical models predict that neutrons and protons dissolve into their constituent quarks, forming a quark-gluon plasma similar to conditions in the early universe. Others suggest the appearance of exotic particles called hyperons, which contain strange quarks and would soften the equation of state, making the star more compressible. The rotation rates of neutron stars span an enormous range, from periods of several seconds down to milliseconds. The fastest known pulsar, PSRJ 1748-2446 AD, completes 716 rotations every second, meaning its equatorial surface moves at roughly 24% the speed of light. This extreme rotation rate results not from the original collapse, but from billions of years of accretion from a binary companion, a process called spin-up or recycling that transfers angular momentum to the neutron star along with mass. The magnetic fields of neutron stars achieve strengths unmatched anywhere else in the known universe. Typical pulsars possess surface fields of approximately 100 million to 1 trillion Gauss, compared to Earth's field of roughly half a Gauss. These fields originate from the compression of the progenitor star's magnetic flux during collapse, amplified by a factor of 10 billion, as the core shrinks from thousands of kilometers to merely 20. The magnetic field lines, frozen into the highly conducting stellar material, concentrate into an incredibly small volume. A special class of neutron stars called magnetars possesses fields reaching 10 to the 15 Gauss, 1,000 times stronger than ordinary pulsars. These fields contain energy densities exceeding 10 to the 25 joules per cubic meter, sufficient to distort the quantum vacuum itself. In such extreme fields, the vacuum becomes birefringent, bending light differently depending on its polarization, an effect predicted by quantum electrodynamics but observable only in magnetar environments. The decay of these ultra-strong fields powers sporadic bursts of X-rays and gamma rays, occasionally releasing more energy in 1/10 of a second than the Sun emits in 100,000 years. The rotation of these compact remnants adds another dimension to their extreme physics, transforming them into cosmic lighthouses that sweep beams of radiation across the universe with clockwork precision. As the massive stellar core collapses from a radius of several thousand kilometers to merely 10, The conservation of angular momentum demands a dramatic increase in rotational velocity. A star that once completed one rotation per month now spins multiple times per second, the same principle that causes a figure skater to spin faster when pulling their arms inward, but amplified to scales that challenge comprehension. The fastest known pulsar, designated PSRJ 1748-2446 AD, rotates at 716 times per second, its equatorial surface moving at approximately 24% the speed of light. At this velocity, the neutron star's equator bulges outward against the immense gravitational pull, creating a slightly oblate shape. The centrifugal forces at the surface nearly balance gravity itself, and any faster rotation would tear the star apart, flinging neutron-rich matter into space. This millisecond pulsar resides in a globular cluster called Terzan 5. Its extreme spin likely the result of mass transfer from a companion star that gradually spun up the neutron star over millions of years, a process astronomers call recycling. The magnetic axis of a neutron star rarely aligns perfectly with its rotation axis, typically offset by angles ranging from a few degrees to nearly 90 degrees. This misalignment creates the pulsar phenomenon, as charged particles accelerated along magnetic field lines emit radiation in narrow beams that sweep through space like lighthouse beacons. When these beams happen to cross Earth's line of sight, radio telescopes detect regular pulses arriving with extraordinary precision. The Crab pulsar, born in the supernova of 1054 CE, pulses 33 times per second, its period gradually lengthening by approximately 38 nanoseconds per day, as rotational energy converts to electromagnetic radiation. The magnetosphere surrounding a pulsar extends far beyond the neutron star's surface, a complex structure of magnetic field lines, relativistic particles, and intense electromagnetic fields. The light cylinder marks a critical boundary where co-rotating field lines would need to move at the speed of light, located at a distance of approximately 48 kilometers times the rotation period in seconds. Beyond this boundary, field lines cannot remain closed, instead opening outward and allowing particles to stream into space along the magnetic poles. This polar outflow carries away rotational energy at rates that can exceed 10 to the 31 watts for young, rapidly spinning pulsars. Within the magnetosphere, electrons and positrons accelerate to energies exceeding 1 trillion electron volts, creating cascades of gamma rays and particle-antiparticle pairs. The electric fields parallel to magnetic field lines reach values of 10 to the 12 volts per meter, sufficient to rip particles from the neutron star surface and accelerate them to relativistic velocities within microseconds. These particles radiate across the electromagnetic spectrum, from radio waves to gamma rays, with the specific emission mechanism depending on location within the magnetosphere and the local field geometry. The radio emission that defines pulsars originates from regions approximately 50 to 500 kilometers above the magnetic poles, where coherent emission processes amplify radiation to detectable levels. The precise mechanism remains debated, but likely involves bunches of particles radiating in phase, producing brightness temperatures exceeding 10 to the 25 Kelvin, far higher than any thermal process could achieve. This coherent emission explains why pulsars appear so bright at radio wavelengths despite their tiny size, their signals detectable across thousands of light-years. Timing measurements of pulsars achieve precision unmatched by any other astronomical technique, with some millisecond pulsars maintaining stability rivaling atomic clocks. The pulsar PSRJ0437-4715 shows timing residuals of merely 200 nanoseconds over decades of observation, making it sensitive to disturbances in spacetime caused by passing gravitational waves. Arrays of such precisely timed pulsars now function as galaxy-scale gravitational wave detectors, searching for the low-frequency ripples produced by supermassive black hole mergers and the cosmic gravitational wave background. Glitches interrupt the otherwise steady slowdown of pulsar rotation, sudden spin-ups that increase the rotation rate by parts in a million before gradually relaxing back toward the pre-glitch trend. The Vela pulsar experiences large glitches approximately every 3 years, each one releasing stored angular momentum from the neutron star interior. The leading explanation involves the superfluid neutrons in the inner crust, which rotate by forming quantized vortices that can suddenly unpin from the crustal lattice, transferring their angular momentum to the observable crust in discrete events lasting less than 40 seconds. Magnetars represent the extreme end of neutron star magnetic fields, objects whose behavior is dominated by magnetic energy rather than rotation. Their fields of 10 to the 14 to 10 to the 15 Gauss contain more energy than the kinetic energy of rotation, and the decay of these fields powers their distinctive high-energy emission. The magnetic pressure in a magnetar exceeds 10 to the 25 pascals, sufficient to crack the neutron star crust and trigger star quakes that release enormous bursts of X-rays and gamma rays. The soft gamma repeater SGR 1806-20 produced the most powerful stellar explosion ever recorded on December 27, 2004, releasing approximately 10 to the 47 ergs in 0.2 of a second. This giant flare briefly ionized Earth's upper atmosphere from a distance of 50,000 light-years, a testament to the extraordinary energy stored in magnetar fields. The event likely resulted from a catastrophic reconfiguration of the magnetic field, similar to solar flares, but scaled up by factors of 10 to the 15 in energy release. The surface of a magnetar experiences stresses that periodically exceed the breaking strength of the crystalline crust, approximately 10 to the 25 pascals, triggering fractures that propagate at significant fractions of the speed of light. These starquakes excite oscillations in the neutron star that appear as quasi-periodic oscillations in the X-ray emission, with frequencies revealing information about the stellar interior structure. Observations of such oscillations following giant flares have confirmed the presence of a solid crust overlying a fluid interior, constraining the equation of state of ultra-dense matter. The decay of magnetar fields proceeds through multiple channels, including ohmic dissipation in the crust, ambipolar diffusion in the core, and Hall drift that redistributes magnetic energy without dissipating it. The characteristic timescale for field decay spans 10,000 to 1 million years, after which magnetars presumably transition to ordinary radio pulses or become undetectable entirely. The population of active magnetars in the Milky Way numbers approximately 30 confirmed objects, Though many more likely exist in quiescent states between outbursts, anomalous X-ray pulsars share many properties with soft gamma repeaters, and astronomers now recognize both as manifestations of the magnetar phenomenon. These objects emit persistent X-rays at luminosities of 10 to the 34 to 10 to the 36 ergs per second, powered by magnetic field decay rather than rotation or accretion. Their spin periods cluster between 2 and 12 seconds, much slower than ordinary radio pulsars, with the strong magnetic fields providing efficient braking that rapidly removes rotational energy. The extreme magnetic fields of magnetars create conditions where quantum electrodynamic effects become directly observable. Vacuum polarization causes the space around the neutron star to behave as a birefringent medium, splitting light into two polarization modes that travel at slightly different speeds. Photon splitting, where a single gamma ray spontaneously divides into two lower energy photons, suppresses emission above certain energies and shapes the observed spectrum. These effects, predicted decades ago but impossible to test in terrestrial laboratories, find their natural proving ground in the magnetospheres of magnetars. The most massive stellar cores face a different fate entirely, one where even the extraordinary resistance of neutron degeneracy pressure proves insufficient against the relentless crush of gravity. When the collapsing remnant exceeds approximately 3 solar masses, a threshold known as the Tolman-Oppenheimer-Volkoff limit, no known force in the universe can halt the implosion. The matter that once formed a star continues falling inward, compressing beyond nuclear density, beyond any state that physics can fully describe, until it vanishes behind a boundary from which nothing, not even light traveling at 300,000 kilometers per second, can escape. This boundary, the event horizon, marks the point of no return for any object or signal attempting to flee the gravitational grip of the collapsed core. For a black hole of 10 solar masses, this horizon forms a sphere roughly 60 kilometers in diameter, smaller than many cities, yet containing the compressed essence of a star that once spanned millions of kilometers. The escape velocity at this boundary equals the speed of light itself, and since nothing can exceed this cosmic speed limit, anything crossing inward becomes permanently trapped. The event horizon is not a physical surface, but rather a mathematical boundary, a one-way membrane in space-time that permits entry but forbids exit. Within this horizon, the known laws of physics strain toward their breaking point. General relativity predicts that all the infalling matter continues collapsing toward a point of infinite density called the singularity, where space-time curvature becomes infinite and the equations themselves cease to provide meaningful answers. Whether this singularity truly exists as a point of infinite density, or whether quantum gravitational effects intervene at some unimaginably small scale, remains one of the deepest unsolved problems in theoretical physics. The Planck length, approximately 1.6 times 10 to the negative 35 meters, represents the scale where quantum effects should become dominant, yet no complete theory of quantum gravity exists to describe what happens there. The space surrounding a black hole warps dramatically, bending the paths of light and matter in ways that create distinctive observational signatures. Photons passing near the event horizon follow curved trajectories, with those approaching within about 1.5 times the horizon radius, becoming trapped in unstable circular orbits before eventually spiraling inward. This region, called the photon sphere, creates a bright ring of light visible in images of black holes as captured by the Event Horizon Telescope collaboration when they imaged the supermassive black hole in the galaxy Messier 87, revealing a shadow approximately 40 billion kilometers across, surrounded by glowing plasma heated to billions of degrees. Time itself flows differently near these gravitational extremes, a consequence of Einstein's general relativity that has been confirmed through countless experiments. An observer falling toward a black hole would experience time passing normally from their own perspective, crossing the event horizon in finite, proper time. Yet to a distant observer watching this descent, the infalling object would appear to slow down asymptotically, its light becoming increasingly red-shifted as gravitational time dilation stretches each photon to longer and longer wavelengths. The falling object would never quite seem to reach the horizon, its image fading to invisibility as the redshift approaches infinity, frozen at the edge of the unknowable interior. Material spiraling toward a black hole rarely falls directly inward, but instead forms a swirling accretion disk, a flattened structure of gas and dust orbiting at tremendous velocities. Conservation of angular momentum forces this material into circular paths, with friction between adjacent layers causing the disk to heat to extraordinary temperatures. The innermost regions of accretion disks around stellar mass black holes reach temperatures exceeding 10 million Kelvin, hot enough to emit powerful X-rays that can be detected by space-based observatories. These X-ray binaries, systems where a black hole strips material from a companion star, provide some of the strongest evidence for stellar mass black holes, with objects like Cygnus X1 serving as prototypical examples since its identification in the early 1970s. The energy released through accretion represents one of the most efficient power sources in the universe. As matter spirals inward through the disk, gravitational potential energy converts to kinetic energy and then to thermal radiation, with efficiencies reaching approximately 40% for rapidly spinning black holes. This vastly exceeds the roughly 0.7% efficiency of hydrogen fusion in stellar cores, making black hole accretion the dominant energy source in active galactic nuclei and quasars, where supermassive black holes, millions to billions of times the Sun's mass, consume material at prodigious rates. Yet the story of stellar death extends far beyond these exotic remnants, for the material expelled in supernovae and planetary nebulae carries the seeds of future stellar generations. The expanding shells of gas enriched with heavy elements gradually disperse into the surrounding interstellar medium, mixing with existing hydrogen and helium over timescales of millions of years. Supernova remnants like the Crab Nebula, visible today as a glowing cloud approximately 11 light-years across, continue expanding at roughly 1,500 kilometers per second, sweeping up ambient gas and triggering compression in neighboring molecular clouds. This compression can initiate the gravitational collapse that begins the stellar life cycle anew. The shock waves from supernova explosions propagate through the galaxy, squeezing regions of gas that might otherwise have remained stable for billions of years. Observations of star-forming regions frequently reveal evidence of triggered star formation, where the expanding shells of older supernova remnants have compressed adjacent molecular clouds past the critical gene's mass, initiating collapse and protostar formation. The Orion Nebula itself shows signs of sequential star formation, with older stellar populations having cleared cavities and compressed gas that now forms the next generation. The chemical enrichment carried by these expanding remnants proves essential for the formation of rocky planets and ultimately for the existence of life. The first generation of stars, formed from the pristine hydrogen and helium produced in the Big Bang, contained no heavy elements whatsoever. These population 3 stars, as astronomers designate them, lived fast and died violently, seeding the early universe with the first carbon, oxygen, and iron. Each subsequent stellar generation incorporated these elements, processed them through nuclear fusion, and expelled still more heavy elements upon death, gradually increasing the metallicity of the cosmic gas reservoir. The calcium in bones, the iron in blood, the oxygen in every breath, all these atoms trace their origins to the interiors of stars that died billions of years before the sun ignited. Carbon atoms forged through the triple alpha process in red giant cores, oxygen created through helium capture onto carbon nuclei, iron assembled through silicon burning in the final days of massive stars. These elements dispersed through supernova explosions and drifted through interstellar space for millions of years before gravity gathered them into the molecular cloud that would become our solar system. This cosmic recycling operates continuously throughout every galaxy, with stellar deaths feeding stellar births in an endless cycle of transformation. The Milky Way currently forms new stars at a rate of approximately 3 solar masses per year, drawing upon a reservoir of gas that has been enriched by billions of years of stellar nucleosynthesis. Each new star incorporates the processed remains of countless predecessors, carrying forward the chemical legacy of generations of stellar evolution. The universe grows gradually richer in heavy elements with each passing epoch, though the rate of enrichment has slowed as star formation declines from its peak approximately 10 billion years ago. Eventually, in the far distant future, the supply of hydrogen gas will dwindle, star formation will cease, and the last stellar remnants will cool toward absolute zero over timescales measured in trillions of years. But for now, in this current cosmic epoch, the cycle continues, with dying stars seeding the birth of new ones, each generation building upon the nuclear ashes of its predecessors, transforming the simple elements of the early universe into the rich chemical complexity that makes planets, and perhaps life, possible throughout the cosmos.